So everyone, welcome to our session, agent-based simulation part 2 session of HSMA today, which, as you may have guessed from the intro, is very much themed around The Sims, which much to the delight of Sammy, at the very least, as I know. Last week we talked, as well as doing some stuff around system dynamics, which is probably best left forgotten by most of us. In the morning, in the afternoon, we explored the world of agent-based simulation, and we said that this is a way in which we can try and model systems in which our behaviours are very important. And we had some great ideas that you started to build up around how you might explore some agent-based simulation for various systems. So today is going to be focused around taking those kind of theories that we talked about last week and seeing how we can actually build an actual agent-based simulation in Python, and we're going to be using a fantastic package called MESA to help us do just that. There's a bit of an intro today where I'm going to take you through the structure of MESA and how we build an agent-based simulation using MESA. But you're going to have lots of opportunity today to actually try out building your own agent-based simulations as well, and hopefully be really interesting to see, as I said last week, whether anybody sort of decides to go with a kind of an agent-based simulation for your project. Just on sort of projects, obviously just a little gentle prod that as we're gradually coming towards the end of the training phase, certainly by the end of today, you'll have covered all of the kind of modelling and data science methods around which you are likely to want to frame a project. The remaining two modules are things that you will likely want to do in your projects, things like version control, developing a web app, some of the stuff that Sammy's going to be covering, like forecasting, etc. But the kind of central primary focus of your projects is likely going to be one of the things that we have covered up to and including today. So hopefully this is now starting to fire off ideas, and you need to be thinking about where you're going to go with your projects. And Sammy's got a bit later, a little bit of input we'd like from you just to find out where people are with that, but more on that later. Okay, so let's go and start our pursuit of MESA. So, as I said, last week we talked about agent-based simulation, or ABS, and we were basically talking about how this simulation approach basically allows us to model this kind of individual level behaviours within a system, the way in which individuals, often people, but doesn't have to be, but individual things within a system are behaving in certain ways, the way in which they are motivated, the way in which they are interacting with each other and with their environment. Really the crucial thing about an agent-based simulation is that we pour all that into our model. And the thing we're interested in is observing what happens at a kind of population level. What's the emergent behaviour, that this sort of system level behaviour that emerges as a result of all these people or all these things doing their own thing and interacting in their own ways. What sort of happens as a result of that? So today, as I say, we're going to have a look at how we can build an agent-based simulation using MESA, which of course is a FOSS Python package. It's really important to stress this. I did mention this last week, but it's a really important point to make, I think, that unlike a lot of the modelling methods that we've shown you, which are much more sort of highly structured, an agent-based simulation is very, very flexible. To the extent where you can pretty much do anything with an agent-based simulation. You typically want to choose an agent-based simulation where the aspect where you kind of want to model aspects of the behaviour within your system, and that's where agent-based simulation really comes to the fore. And you're kind of interested in what happens when we kind of chuck in a population of people all doing this. What then happens at a system level, and that's really where you tend to use it. But it can pretty much do anything you like. the package that I'm going to show you, MESA, I mentioned last week I don't really like packages, framework packages for agent-based simulation generally, because they are sort of hugely flexible and you can do anything, so they tend to end up just limiting you. MESA is a great example of something that is far more flexible. So MESA basically just gives you a few sort of handy shortcuts that help you to build up an agent-based simulation. So it already has concepts of what an agent is and what a time step is, and you don't have to sort of code all that from scratch, which you could do. And indeed, when I did my PhD, I coded the agent-based simulation from scratch to define what it was. So you can do that, but MESA just gives you sort of some little starters, little helping hands. However, you may choose not to use all the elements of MESA if you're doing an agent-based simulation, or none at all. It depends on what you're wanting to do, but it can just help you a little bit to structure things. So let's talk a bit about MESA. So there's a link to MESA here, which has a lot of information, documentation about the package, as well as a tutorial, which I'll come back to later. I'll mention their own tutorial. In the unlikely event that any of you have used MESA before, be aware that it has changed quite recently and quite significantly. I found this out when I was writing updating the training this year, and wondered why nothing worked, and it's because they completely changed the way it works. The joys of modelling and data science is that everything changes, apart from SymPy, which is one of the most stable packages I've ever seen. But it has quite significantly changed. Basically, it's just kind of a framework. It gives us that framework to allow us to more easily build an agent-based simulation in Python. And it also comes with some pretty nice analysis and visualization techniques out of the box that can be really nice if we're building agent-based simulation models. We can watch how those models play out and explore the results that we get out of those models too. So this morning, to demonstrate how MESA works and how it's kind of structured and some of the features that you can use within MESA, what we're going to do is we're going to start by building a relatively simple agent-based simulation model. Okay, so this is the model that we're going to try and build up. So in our model, we've got basically HSMAs. I've called it the I Love HSMA model, and we've got HSMAs who are our agents, and they basically randomly talk to each other on Slack, and Slack represents our environment, and we're going to represent HSMAs randomly talking to each other on Slack as HSMAs basically moving around a grid of cells. So our grid of cells, our environment here, is going to represent people sort of randomly encountering other people on Slack. So at the start of our model, some of our HSMAs are going to love the HSMA program, and some are going to absolutely hate it. And there is absolutely no in between in this version of the model. They either love the HSMA program or they hate it. And in a model, what we're going to do, when HSMAs start talking to each other, they encounter each other on Slack, there's a chance that their opinion might influence the opinion of the HSMAs to whom they are talking, if it happens that they have different opinions from the person they're talking to. And to kind of capture that, each HSMA also has a kind of persuasiveness that basically determines how likely it is that they will change the opinion of the person they're talking to if that person has a different opinion from them. And so we're imagining that we want to build this model in order to allow me to model how these persuasion behaviours might influence the number of people who love and hate HSMA over time, and also allow me to explore the potential effects of, for example, doing things like, well, maybe I could seed more people at the start that love HSMA, or I could, this sounds very sinister, I could do things to change how persuasive they are. I don't know what those things are, but let's just suspend our disbelief for a moment. Let's imagine that I want to use this in some way to help more people love HSMA, so I want to get a better understanding of how my system works. And this is a great example of an agent-based simulation where I'm basically coding in the kind of the behaviors of what each individual is doing and how they're interacting, and then seeing how that plays out, chucking them all in the box and seeing how that plays out. That's an example of an agent-based simulation. So how are we going to code this? So basically, there's a kind of basic structure to the way in which we set up a MESA model, and generally we have either one or two .py files. The first .py file is we have to have, and the second one's optional, but we're going to be using it initially this morning. So the first .py file is going to basically contain the bulk of our model. It's going to contain a definition of what that model looks like. It's going to contain what our agents are and how they do their thing and how everything works, basically. So that .py file will contain, it'll be structured in an object-oriented way. So this is agent-based simulation, as I mentioned earlier in the course, is a fantastic way to really get your heads around object-oriented programming. And I think if you've been struggling a little bit with object-oriented programming, which is understandable because it's a bit, especially if you're not a coder, it's a bit odd, and even some coders struggle with object-oriented programming. Agent-based simulation, I would argue, is a really nice example of where object-oriented programming is so useful. And hopefully a lot of you will find, oh, okay, yeah, that makes sense why we're doing it in this way. So in our PY file, we're going to have various class definitions. The first class definition is going to be a class definition for our agent, describes what an agent is. If we've got more than one type of agent, which you can have in an agent-based simulation, we would have a class definition for each type of agent. But just for our simple model here, we're just going to have one type of agent. However, when we explore things a little bit more this afternoon, you might choose to have more than one type of agent. So within our definition of our agent, we're going to have, because it's object-oriented programming, so we're going to have a constructor. Remember, the constructor is the thing that assembles the object, so it defines what kind of the default values will be when that object is created and how it will be created. So that will set up the default kind of attributes of that agent. We're going to have the agent will have a method for each behavior that we want to model. Remember, our agents have various behaviors. That will include a movement behavior if we want our agents to move in our environment, which we do for this model that we're going to build, because effectively we're representing movement in our model represents sort of moving around different channels of Slack and encountering people. So it's a more abstract kind of movement. It doesn't always have to represent physical movement. We're also going to have a step method, and that step method basically will define what an agent does at each time step. Okay, so what you set up a constructor that's compulsory because that you have to set up the default parameters. A step method, which is also compulsory, you have to have one of those if you're using MESA. And then a number of behavioral methods. And basically what your step method will do is say, okay, I want you to do this, and then maybe move by calling this function, and then maybe do this by calling this, etc., etc. So that's our agent class. And as I say, if we've got more than one type of agent, we would have more than one agent class. And then we'll have a single class definition, which represents our model. And that class definition will also have a constructor. And that constructor will basically set up the model. It'll set up the agents that we want to live in that model. It'll set up the environment in which they're going to exist. And these things called data collectors, which I'll come back to in a moment. And the model will also have another method called a step method. Again, just as with the agent, each agent has to have a step method. The model has to have a step method as well. And basically the model step method defines what the model does at each time step. So the agent step method says, me, as this agent, I need to do this, and then this, and then this. The model step method basically is the model controlling things, saying, okay, I need to control things in this way and then this way. And usually the model step method is much simpler, as we'll see. And then, in addition to those class definitions, we will likely want some standalone functions that we basically define to kind of specify how we collect various data over the course of our run. So the kind of outcome measures, the results that we're interested in. And this will make more sense when you see it. So that's basically our main py file. It's a class definitions for our agents, a class definition for our model, and some functions that describe how we want it to collect the results we're interested in. That's at its core a MESA model. Optionally, we can have this second .py file, which will represent a visualization server, which will basically allow the model to visualize our model so that we can watch it play out over time and watch what our agents are doing and all that kind of stuff. And we don't always want that, but sometimes we do, and sometimes that's really useful. So the first run through the model, we're gonna do this because it's particularly when you first build a model, it's really useful to see how it works. So that py file is going to contain basically a function which will define how we draw our agents, how we want them drawn on the screen. It'll have a visual representation of our environment, in this case Slack. It'll have a dictionary which will basically contain all our model parameters that we want to pass in to the model when we set it off running. And that will also include some user interface elements. So we could have things like, okay, well, the number of agents, I want that to be a user settable parameter. So the user can choose how many agents. And we can do that really easily in MESA. We will also can have an instance of the visualization type that we want, and that will make more sense when we see that, and that'll bring everything that we've defined in here together, and then basically a simple command that shows the visualization. So that sounds quite complicated, but when you see it, you'll see actually it's fairly straightforward. Okay, so let us start by building our main model file and gradually build up our agent-based simulation. So the code that I'm taking you through here, you've got available in your repositories. It's the model. It's in the HSMA love hate model directory, and it's the HSMA love hate model.py file. I'm going to be talking through. I'm going to talk through bits of the code piece by piece here. But just be aware that, and you'll have time when we come to the first exercise in your groups to look back over this code as a whole and make sure you kind of understand everything. But I'm just going to take it piece by piece here just to explain how everything works. So first thing we do, no surprise, because this is what we always do when we start any Python code, is we import the libraries we need. In this case, that's we're going to import MESA. We're also going to import some specific things from MESA so we can refer to them directly. So from MESA, we're going to import the classes of agent and model. So that means that we can lean on the fact that it's already defined what an agent is in an agent-based simulation and what an agent-based simulation model looks like. We're also going to import from MESA.time this thing called random activation. This basically allows us to randomly decide which agents act in which order, and we'll come back to that. From MESA.space, we're going to import something known as a multi-grid. This is basically just a type of grid in which more than one agent can be in the same cell. So multiple agents in the same cell is a multi-grid. And that's what we want here, because our cells essentially represent sort of people talking to each other. So we want that to happen. And we're also going to, from MESA.data collection, we're going to import this thing called a data collector. Again, I'll come back to what those things are in a moment. And of course, we'll also import our old friend random, the random library, because that's so useful whenever we're really doing any modeling or data science. So those are our kind of import statements. So I said the first thing we need to do is to define our agent classes. We've only got one in this simple model, and our agent in this model is an HSMA. So let's set up the constructor for this agent. So we define our class in the normal way, in an object-oriented way. I've called it HSMA underscore agent. Now you'll notice here that in the brackets I've passed in agent. You'll recall from here we imported the class agent from MESA, And hopefully you remember back from the object-oriented programming training many months ago that when this happens, this is known as inheritance. So this allows us to say my HSMA agent class is a child of this class of agent. So basically, rather than having to define, what this allows us to do, rather than having to define what an agent is in an agent-based simulation from scratch, we don't have to do that. We can essentially inherit from the agent class that MESA has already written for us, and say it's one of those, basically, with these twists. And that's what we're going to do. So we pass in, very simple to inheritance in Python, we just pass in the name of the class we're inheriting from. Then we set up our constructor here, which is going to assemble everything together. So the things that we're going to pass into the constructor, we need to pass in self. Remember, self is just kind of a copy of me, as in this instance of the object. We have to pass in for MESA agents, so anything that inherits from a MESA agent, we have to pass in these two things here. I mean, you can call them whatever you like, but it needs a MESA agent needs an identifier, some sort of numerical representation of an agent. I think it has to be numerical. Double check that. But some sort of ID for that agent, and you have to pass in the model in which the agent exists. Those two things are compulsory. Okay, so you have to, if you're inheriting from a MESA agent, each agent must have an ID, and you must give it the model in which it lives. Anything after that is then stuff that we want to add into our agents. Okay, so here I'm going to pass in, when I create an agent, I'm going to specify an initial probability that they love HSMA, so I can decide whether or not this HSMA at the start loves HSMA or whether they hate it. And I'm also going to pass in what I've called persuasiveness max, which is basically just a maximum level of persuasiveness. So when I work out how persuasive this HSMA is going to be, that will be the maximum level of persuasiveness that they can be. So that's unique to my problem. Self you have to have because it's object-oriented, and then these two things here, unique ID and model, we have to have because we inherit from a MESA agent. Then we call, the first thing we do, because this is inheritance, if you recall from your object-oriented training, we can do this rather snazzy thing where we can say, well, we're inheriting from agents, so call the constructor of the parent class, the MESA agent, do all that stuff first, and then do all these things that I want you to do. And we do that by calling super.init. And we have to pass into that constructor the two things I said we need. A MESA agent has to have, which is an identifier, which I call a unique ID, and the model in which it lives. So that will do, MESA will then do its thing and say, okay, right, I've set up an agent of type MESA agent. Then all of this is stuff that is unique to my HSMA agent. So I'm going to basically, when I create a new agent, a new HSMA in my model, I'm going to first determine whether or not they love or hate the HSMA program. I've passed in, when I create a new agent, I'll give it a probability that they love HSMA, and I'll just do a simple check by using the uniform distribution. Random pick a number. If it's less than that number, then they love HSMA. If not, then they hate it, basically. And I'll set this attribute called love HSMA to true or false. So just a simple Boolean to say whether they love it or not. The other thing I will do when I create a new HSMA is I'm going to randomly determine that user's persuasiveness. Again, I'm just going to draw it here from the uniform distribution. And so their persuasiveness can be anything between 0 and up to whatever I passed in as the maximum level of persuasiveness. Okay, so it'll just randomly pick. So whenever you create a new agent in this model, it'll randomly work out whether they are they love HSMA or hate it at the start, and how persuasive they are. Those are the two things that it's going to do. So that's our constructor set up. Now we need to think about our various behaviors, and it's always useful to think, okay, do I need my agents to move in my environment as a starting point? And I do in this particular model. I want them to be moving around Slack and encountering other HSMAs. We're going to add a movement method to our agent class. So I've just called it move. I could call it anything I like, but I've just called it move. And basically, what this method's going to do here, the first thing it'll do is work out where it can. No, so before I say that, um, it's important to note the way this is structured. This is the movement method. This will only be called if it's determined the agent is going to move. So if this is called, you're assuming that the model has said, right, agent number 462, you have to move now. So assuming they're going to move, we can write the instructions. So the first thing we want to do if we're going to move is we're going to grab all the possible locations it could move to. Okay, the way we can do this using MESA is we can actually use the get neighborhood method of the grid object in a model, in a MESA model. And if we call self.model.grid.get neighborhood, it will basically return all of the cells, all the cell references that are in the neighborhood of our of a cell reference that we give it. So if we call the get neighborhood method, if we pass in our current location, so this is self.pos basically means me as an agent, where am I now? The agent that's going to be moving, where am I? I'm going to pass in this attribute here, more equals true, which basically means I want you to use a more neighborhood. A more neighborhood, if you recall from last week, is one in which on a two-dimensional grid, a more neighborhood is the 8 cells that surround it. So northeast, southwest plus the diagonals. You can also have a von Neumann neighborhood, which is just up, down, left, and right. It doesn't include the diagonals, but we do want to include the diagonals here for whatever reason. So we say more equals true. And here I said include center equals false. So the center is where I am now. That's me as the agent, the one that's going to be moving. You can choose to have that as a valid movement location. However, because of the way I'm structuring this, that this movement method will only be called if we determine that we want the agent to move, then I don't want to include the center because I actually want them to move, and I don't want your current location to be a valid location you can move to, because that would be equivalent to not moving. So I pass in where I am now, that I want the neighborhood to be a more neighborhood, so the 8 surrounding cells, and I don't want you to include the center where I am now. So that will basically return a list of cells that are potential locations. We can then just, because it's a list, we can just randomly choose one of those cells using random.choice and select one of those locations. And then we can tell it and again, this is where MESA comes in. We can say, right, the model, I want you to move the agent on this grid. So if I call model.grid.moveAgent, if we call that method, we just pass in the thing we want to move and where we want it to move to. So in this case, the thing we want it to move is me. Remember, this is me as an agent. I've been told to move, so I need you to move me, and I want you to move me to this new position, which is the one that was randomly selected for me out of all the possible neighbours. Okay. Conscious that's quite a bit so far. So, Sammy, are there any questions that have arisen so far?
So the main one that came through was just checking about the import of, so we've imported all of MESA, but also imported the separate parts. So just to kind of clarify there, I think we gave the conclusion in the chat. That's just so that you don't have to keep doing MESA.time.random activation, etc. every time you want to use that. So that was the main one. And the only other thing was just about object-oriented as well, just in a more general sense. People kind of querying, is object-oriented, if they're not feeling that confident with where they could use object-oriented at this point in time, what's our thoughts on that? And I'd say at the moment, object-oriented makes so much sense for things like MESA and discrete event simulation, but I don't think don't feel worried if you're not using object-oriented for all your code. It's perfectly fine. It often doesn't make sense to use object-oriented. You might be overcomplicating your code just for the sake of using it, but here it's the practice you have today will help you see opportunities to use it in your own code as well, I think.
Yeah, so for agent-based simulation, it's essential. You will have to do it. You can't.
Yeah.
Couldn't, but you're right. For other things, it is less essential. So, but the nice thing about MESA is that it is always structured in the same way. So you can build out an agent-based simulation always using this kind of framework, and it will work in that way. Yeah, apologies. I should have. I mean, we've done this a few times. I should have flagged it up a little bit more, really. So this basically is import MESA, and technically we could just do that. But then every time I'd need an agent, I'd have to say MESA.agent. It's the agent that lives in MESA. It's the model that lives in MESA, and that gets quite frustrating. So if there are things that you're going to be referring to time and again, you can do this. Say, well, from this. Import this, which if you can also do that if you only need bits of a package. So if the only bits of MESA that we needed were these bits, we could get rid of the import MESA entirely. That's not the case here. But it does allow us to say, we can just say agent now, and it knows, oh right, yeah, that's a MESA agent. Because we've defined it here, so that you'll see this quite a bit in various code. It's mainly to stop us having to, as you can imagine, this would be much more complicated, or look much more complicated if we had to say MESA dot every time. Okay, so we've talked about the constructor and we've talked about the movement method. So what other behaviors do I want from my agents? Well, as well as moving around Slack, in other words, encountering random people on Slack, I also want them to talk to other HSMAs. And it's through that talking that they might potentially influence the opinion of others. So I'm going to write that as a separate method, and I've just called it talk. So our agents can basically move and they can talk. This talk method that I have here, again, we pass in self because we need to pass in a copy of the object to any methods that we write. What this method is going to do is it's basically going to check first to see if there are other people. Is there anyone around to talk to? Okay. So the way in which we're representing this in our kind of abstract grid is, are there other HSMAs in the same cell as me? In other words, and that will be used to represent, are there other people around to talk to? So the first thing I can do here is to get a list of all the agents in the cell where I am now. Okay. And again, MESA gives us a handy shortcut for this, because we can grab out the get cell list contents method of the model.grid, and that will basically splurge out back to us a list of all of the agents that are in that particular cell, if there are any. Okay. So here I call that function, and the cell I want to look at is where I am now. It's where my particular cell. So that's self.pos basically gives the location of me, my cell. You have to pass it in as a list. Just be aware of that, even if you've only got one item, which often you will. So we say, okay, I want you to get all of the people, all of the agents who are in the cell where I am now. So that I've stored that in a little list called cellmates. Now what I want to do, I'm first of all going to check if there are any other agents here. So an easy way to do that is just see if the length of that list is more than one. If it's not, then I'm the only person here, and there's no point doing anything else. I'm not going to talk to myself. So nothing else needs to be done if it's just me. But if there are other people here, then we need to proceed. So if there's more than one agent here, then somebody else is here as well as just me. So then I'm going to go into a for loop. I'm going to say, well, for each inhabitant in cellmate, so in other words, for each agent in this list here that you found, first of all, I want to check if they've got a different opinion to me. So if the inhabitants love HSMA attribute, remember that's an attribute we set up at the start for our agent, and it's a Boolean, true or false. If that's not equal to my love HSMA attribute, so doesn't matter which way around, but are they the same or are they different? So if it is different, then we will do this. If it's the same, then we won't. Because of course, if it's the same, then I can't persuade them in any way. We both either love or hate HSMA. If it's different, then I will essentially randomly determine whether I'm going to persuade them or not, change their opinion to mine. And I'm just, again, going to use the my persuasiveness that we set up at the start, which is stored as an attribute against me. I'm going to randomly pick a number between 0 and 1 and see if that's less than my persuasiveness. And if it is, then I will say that I have persuaded that HSMA. In other words, that HSMA now thinks the same as I do. So if I hate HSMA and the other agent loved HSMA, and it's determined here that I am going to persuade them, then I will set their love HSMA attribute to the same as mine. Okay, so that's persuading them. Incidentally, obviously, as you go through this for loop, one of the inhabitants will be me. That's okay because by definition, my love HSMA attribute has to be the same as my own love HSMA attribute, so this will never run. If that makes sense. Okay, so it's just a shortcut there. I don't have to worry about the fact that one of the inhabitants will be me. I don't have to do anything like give it my ID and say to ignore that one. I don't need to do that because one of the iterations through the for loop will be me. It'll say, okay, that's me. Do I have the same opinion as myself? Yes, I do. In which case, don't do anything else. So we've set up our agent. We've set up our constructor. So that when an agent's set up, they get we randomly determine if they love or hate HSMA and how persuasive they are. Then we set up a movement method, which basically said if you're going to move, look at the 8 cells around you and pick one at random and move there. And we've set up a talk behavior as a separate method. And we've said basically check whether there is anybody else in the same cell. And then if they've got a different opinion to you, you might persuade them. And that will change their opinion to mine. So that's all the behaviors that I want to model for my agents. The only other thing I need, which we must have if we've got a MESA agent, is a step method, and it needs to be called step. So I've defined a step method here, and basically this will define the order in which each agent will perform its actions and when it should perform those actions at any individual time step. So each agent's step method will be run each time step. That will be the method that gets run, and that in itself will then run other things. Okay, so this step method, MESA will say, okay, agent number 472, it's your turn, let's run your step method. And this will define what we want that agent to do when it's their turn. So the first thing I want them to do is basically work out whether or not they're going to move. So here I've just got some very simple logic to work out whether they're going to move. I'm just going to basically flip a coin, 50-50 chance whether they move or not. Obviously in your models, depending on what you're representing, you may have something a bit more elaborate to work out whether an agent's going to move or not. Here I'm just flipping a coin. So I just say random choice on the list, true and false. If that happens to be true, then we've decided you're going to move. So call my move method. So we've already defined how to move. So just call that method. And then regardless of whether or not the agent moves, it should begin its talking behavior. So call the talk method. Okay. And obviously the talk method may determine, oh, hang on, there's no one here. I won't talk. So basically all the agent step method is doing is saying, flip a coin to decide whether to call the move method or not on this agent. And then regardless, call the talk method. But this is the method that will get run by MESA when it's this agent's turn. This will happen. So it'll flip the coin, then it might run their move method, and then it will run their talk method, and then it'll move on to the next agent, and they will have their turn, etc. Okay, so that's the agent class. We also need to write a class for the model. So again, we have to start with the constructor. So in our model constructor, we're basically going to set up the environment. We're going to create something known as a scheduler. And so the scheduler will basically decide which agent acts next. So which one, whose turn it is basically, and tells them to do it. In other words, run the step method that we've just written. Then we're going to create our agents and we'll add them to the environment and to the scheduler. And then we're going to create this thing called a data collector, which I keep saying I'll tell you about what that is in a moment. Basically, a data collector is an object in MESA that allows us to collect both model-wide and agent-specific data, and basically allows us to essentially model results, monitor results over time. And this will make more sense when you see an example of this in a moment. But that's what a data collector is. It basically collects. It says, okay, First time step, let's see how many people are in this state, how many things of this we've got. It collects that data for you. So let's have a look at the key constructor for the model class. So I'm going to do that by looking, because it's a little bit longer, I'm going to do that by looking in the code file itself. So I will zoom this in, apologies. Look, there we go, so hopefully that's a bit easier to read. So this is my model. I've called it the persuasion model. You can call it whatever you like. But again, it's inheriting from the MESA model class. So we pass in model in the brackets there. Then I set up my constructor. So the things I'm passing into the constructor are self, the copy of me. We always have to do that. I'm then going to pass in what I've called n. So n basically just represents how many agents I want in the model. We're going to pass in a width and height, so that will be the number of cells wide and tall in our environment. And then I also need to pass in anything that I will need when I'm setting up an agent. And remember, we said that an agent, when we create a new agent, will give them a probability that they initially love HSMA and will tell them what their maximum persuasiveness is. So the model's going to need to do that, so we need to pass that over to the model first. So the model, we give to the model, you're going to need to pass this over to the agents when you set them up. The first thing we do in this constructor is to write this line of code here, self.running equals true. Do not worry about this. You just know you have to write that. Always write self.running equals true. It's basically a line of code that's required for something known as the batch runner, which we'll come back to later this afternoon. But just put it in. It's just easier just to type self.running equals true as your first line in your model constructor. Then we're going to set up the number of agents as an attribute of the model. So we've passed that in as n, so I'll store that as number of agents. I'm then going to set up a what's known as a toroidal multigrid. So remember, multigrid we imported at the start, and we said a multigrid is basically a type of grid where we can have more than one agent in the same cell, which we need for our model. Otherwise, nobody would ever persuade anyone else. Toroidal basically just means that it wraps around. Okay, so if you've got an agent who's on the far right of the grid, and then they move right, they will appear over to the left. Similarly, if they're right at the top and they move up, they'll appear at the bottom. It's like Pac-Man, basically. That's all a toroidal grid is. And so the true Boolean, this third parameter here, that switches that on. So if you don't want that, you would turn it off. But you need to think about what your grid represents. And obviously, in a lot of cases, we've got abstract. So here I'm essentially just mapping random encounters on Slack. So it kind of makes no sense to have a border. That doesn't really make sense to me. So I'm going to switch that off. So I'm going to have a toroidal multigrid here. And in setting up that a multigrid, I just need to pass in how wide and high it is. And we pass that in when we create the model. I'm also going to set up a scheduler. So remember, the scheduler is the thing that basically determines which agent runs next and runs their step methods. And you'll also remember that I imported such a scheduler at the start. I called it called the random activation scheduler. That's a type of scheduler where it basically says it just randomly pick which agent goes next on this time step. So each time step in your model, all of the agents will have their turn, but the order in which those turns happen with a random activation scheduler will be completely random. So it will just randomly say, okay, agent 621, you're next. And it'll run that. You need to think about what... so if, for example, you were modelling a disease progression and you had kind of the spread of a disease, that might be quite important whether the order in which agents act. Because if this agent here is infected, and then they're about to move into a cell with an uninfected person, if they get to act first, that will infect the other person. If the person who is not infected acts first, they may well move away first. So it can be important. However, I would also say that in most cases, you probably do not have information about the order that you could adequately make an assumption about. So if you do not, then I would say random activation is the way to go. You don't know which order agents would act in, so you're just going to pick that at random. Okay, so probably most of you will be using this for your scheduler. Then we're going to create our HSMA agents, and we've passed in the number of agents we want. So we're just going to have a simple for loop that goes up to that number of agents. And each time it'll create a new agent object, which remember we've defined above in our class definition. We called it an HSMA agent. And remember the things we needed to pass into that were an ID. So I'm going to use for the ID for this agent just the iterator value in the for loop. So the first agent will be agent 0, second agent will be agent 1, etc. Remember the other thing that you have to pass into something that inherits from the MESA agent object is a copy of the model. Now, I'm in the model here, okay? This is the constructor for the model. So the model in which the agent is going to live is me. So to pass it the model, I pass it me. Okay, so that's why it says self there. So it can be a bit weird to get your head around that, but you have to think whenever you're writing object-oriented programming, where am I now? Who am I as I'm writing this? Here, I am the model. I'm going to be an instance of this model, and so the instance of this model is where I want my agents that I'm creating to live. I want them to live in me, so I pass me, and that's self. So I passed in the ID, a copy of me, and then remember the other two things were we had to pass anything that was unique for our particular agents, and that was this initial love probability and the persuasiveness max, which we passed into the model. So we give it to the model, and then the model gives it to the agents when it sets them on. Once we set up our agent in this for loop, then we will add it to the schedule, the scheduler, which we've set up above. We created the scheduler as being a random activation one. So we just call the .add method on that schedule and pass in the copy of the agent we've just created. Then what I'm going to do here, I need to work out where I'm going to place them on the grid. The logic that I've put in here may differ to whatever you do. What I've decided to do is to say, okay, I want my agents to kind of be spread out if possible. So I want them to start where, ideally, in an empty cell, so they're not with anyone else. And then if you can't find an empty cell, then just basically pick any cell at random. And that's all this bit of code here is doing. And it uses a try except structure, which remember this allows us to say try doing this. If that throws up an error, in other words, you can't find an empty cell, then run this instead. So that's what this does. It just uses a couple of MESA methods to say, give me an empty cell, put them there. And that will work as long as we've got more cells than we have agents. If we've got more agents than we've got cells, then obviously eventually we'll run out of empty cells and we'll have to start just putting them in a cell that's already occupied. So that's all I'm doing here. But that's, I've just decided to do that as part of my model. And the last thing we're going to do in our model constructor is to set up a data collector that can basically collect agent-specific and model-wide data. And here we're going to set up a data collector, and a data collector can have model reporters, and model reporters are things that collect data across the model, and we have agent reporters, which are things that collect data about individual agents and their attributes. It can be a bit, the lines can blur, as you'll see. We're not going to have any agent reporters here, but we still have to specify an empty dictionary. But we set up these things as dictionaries. So I'm going to have two model reporters. One I'm going to call total loving HSMA, one called total hating HSMA. And basically what these things are going to do is it's going to calculate how many people at the moment love HSMA, how many people hate HSMA. That's all it's going to do. And what we do is we do them as a dictionary. The key is what I want to call this data collector, and you can call it anything you like. It comes in as a string, but you'll refer to that by name later. Excuse me. And then the value against that key is the function that I want to call. So when I tell you to calculate the total loving HSMA, I want you to go off and run that function to do that. So you remember I said that we'll have some standalone functions. You'll see in a moment some standalone functions in this file. One will be calculate the number loving HSMA, one will be calculate number hating HSMA. So that's our model constructor. We set up a grid. Set up the number of agents. We set up the grid. Set up the scheduler. Create our agents through a for loop. Shunt them in the scheduler. Put them on the grid, and then start off our data collectors. Set up our data collectors. The only other thing that we need in our model class is a step method. So remember, the model also has to have a step method. All that our model's step method will do is tell the data collector to collect the data we've asked for, and tell the scheduler to go forward by one time step. So the way a MESA model works is it will run the model, and by running the model, it will, at each time step, it will say run the step method of the model class, which is this, and that in turn you will then run the step method of the scheduler, and the scheduler will say, hey, Agent 47, it's your turn now to act, and it will run Agent 47's step method. Okay, so the MESA will run the step method of the model, which in turn will run the scheduler, which in turn will run the step method of each agent. Hopefully that makes sense. It's a bit weird, but if you sort of think about it sort of from the top down. So this is all it's doing. We just tell the data collector that we've set up in the constructor, tell it to collect, and you have to pass in the model from which you want it to collect. And remember, that's me. I am the model. And we need to tell it to ask the scheduler to step forward one time step. So self.schedule.step. Most of your models, if you're doing simple models at the outset, will probably copy this code almost verbatim, because generally that's exactly what you want to do. But you may have other data collectors that you want to enable, and you might have something else you want to do. But generally, these are the two things that you do. So we've defined our agent class. We've defined our model class. The only other thing that we've got to do is to write these standalone functions that I keep talking about. These are the ones that we've now referenced in our data collector. We said to data collector, when I tell you I want the total people loving HSMA, I want you to run this function that I've called calculate number loving HSMA. So basically what it will do, it'll say, okay, I need to go and calculate the number of loving HSMA. How do I do that? I'll run this method that you've called calculate number loving HSMA. And you'll see this is very simple. Basically sets a counter to 0, goes through a loop, checks if they love HSMA or not, and adds 1 if they do, and then returns that number. That's all this is doing. And it's doing exactly the same for hating HSMA. Okay, so that's all these methods are doing. The point is that you can define any logic you like in these things, so it gives you a lot of flexibility to grab whatever outcome measures you like from an agent-based simulation model. So you can literally do anything. I've just done something very simple, just count. So every time step, the data collector will whir into action, because the model's step method will say, data collector, do your thing, and it'll collect the information we specified here. So it'll run both these methods, and it will say, okay, time step 1, there are 27 people that love HSMA and 48 that don't. Okay. What was the point I was going to make there? Oh, yes, sorry, I forgot to mention that. You also have to, in these standalone functions, you have to pass in a copy of the model on which you want them to work. So don't forget to add that in. Basically, that's what I was going to put it. Right, that was a lot of stuff. I've got to go through the server file, although that's much easier. Sammy, are there any sort of questions that have arisen about any of the model file, which is the main bits, really?
So I think I've answered most of them. There was a question about whether it's possible to have simultaneous actions. I believe MESA does support this. There is a simultaneous activation that would be the alternative to the random activation, but I don't know if you've got any thoughts on whether that's a
So,
cool.
yeah, I mean, so I would. I guess my initial. I mean, that's great. That's. I'd definitely check that out. But my gut instinct to that would be very careful about going down rabbit holes like that, because that imply you're starting to get. This is not like a discrete event simulation model where people come in a nice order and they queue up, and then this thing happens to them, and then one of these things happens to them, and it's highly ordered. An agent-based simulation is a lot more fuzzy than that. You are capturing aspects of behavior. Very often, you don't want to go down to that. You want broad brushstrokes generally. You probably, because in doing that, you are then making an assumption that these things absolutely do happen simultaneously. Whereas if you're just assuming that there's the kind of noise in the system, randomness, it kind of gets you around that. So it's good that that's there, but just be aware that you may not want to go down to that level of detail unless you are certain this is how your model operates. So just be aware of that.
Perfect. Next one is, I think, this may become a little bit clearer as the day goes on and people have a chance to play around with models. And I know you do cover it a bit more in the afternoon as well. But there was just a question about struggling to translate the idea of the lattice into the real world. So just looking for a bit of clarity, is that essentially the environment and the cells as things like different healthcare settings or different fairground rides or different seats in a waiting room? And also, how does that impact the number of different locations you can move to? Does that mean you can only move to one of the sort of 8 locations in the neighborhood in a single step?
So I will come back to this later. Do not get hung up on the grid. You don't actually have to have a grid at all if you don't want one. Okay. A lot of people get hung up, understandably, with this idea that then, okay, an agent-based simulation, everybody lives in a grid. A lot of agent-based simulations do use grid structures. You do not have to. Remember, an agent-based simulation, you can do anything you like. So you do not have to have a grid representation. Often it's quite useful, and you can just think about what your grid represents, and you can specify whatever rules you like for moving around that grid. And your grid could be as simple as there are 3 positions in this grid. This represents being in this state. This represents being in the hospital. This represents being at the. You could have it as simple as that. And I'll mention it again later. But the my PhD model, the Bumblebee model, did not use a grid. It used a grid for the visualization, but I didn't use MESA. I don't think MESA was around at that time. But that was just a convenience for drawing some squares on the screen. It did not use an explicit grid as an environment. It just had this idea: there are 6 fields in the environment, or however many fields, and each one has some flowers in it. And I defined that. Your environment can be anything, so don't get hung up on trying to squeeze everything into a grid structure. If it makes sense to do so, then it gives you some handy shortcuts. But do not worry about if you're. Don't think I have to only think of problems that I can think about in a grid. That is not the case. Okay, so I'm using a grid because that's a simple. A lot of agent-based simulations will show you a grid structure as a kind of initial intro, but you do not have to use them. So just be aware of that. And that goes back to what I was saying about, there's lots of things that makes it you may choose not to use all of them. And that's an example of where you don't have to. You might just say, okay, I just need to know what an agent is and what a model is. And that's as far as you go. So yeah, don't get hung up on that, but we will come back to that later.
Brilliant. Next question that came through is there a sync for agents, or do they just keep getting added?
So again, it's not like a discrete event simulation where there is such a concept as a generator and a sync. But you can do anything you like with an agent-based simulation. So you can remove agents and you can add agents at any point. And how you do that is entirely up to you.
Brilliant. And the final question that's come through is, did you need to write a scheduler step method? If not, why not?
No, because the schedule has its own. So this is what MESA is doing. So MESA, when you set up, I want this kind of scheduler. In this, we're using a random activation one. That's all predefined, so it knows the random activation scheduler knows I need to call. You give me a model which contains some agents, and I will go to each of those agents and call their step method. That's what it does. And it'll do so in a random order if it's the random one.
Brilliant. Thank you. I think that's everything that hasn't been answered in the chat. So
Okay, cool. Uh, so a lot of this I think will make more sense as we go through, and you see this code a bit more. But my overall advice is don't get hung up on things with database simulation. You can do anything you like. Okay, this is just a kind of a very loose structure that you can pin things around. If it does not make sense to hang it around a grid, or it does not make sense to do this, is not. This is the hardest bit. Okay, I would say that it is very, and I've tried to frame today's exercises around this. It is not like a discrete event simulation where you say, you always have this concept of a queue, that you're queuing for things and you can do X, Y, and Z, and there's lots of different things you can do, but there is a constrained set of things you can do. Agent-based simulation has no constraints. You can do anything you like as long as you've got a concept of agents, individuals that are doing things, and they exist in some form of environment. That's it. That's all you need for it to be an agent-based simulation. Everything else is entirely up to you how you do it. So that was the model file. I'm going to gloss over because we're running over slightly, and I'm conscious there's a lot of information to take in. The other file I mentioned was the server file. You're going to have a chance in the exercise to look over the code for this anyway, so I'm just going to go over this fairly rapidly, just talk you through the generalities of it, and then you can have a proper look in your groups. So this is a separate .py file that we set up, and you'll see it in the repository as HSMA love hate server.py. Again, we start with our imports. So I basically import the from the file I've just written. I import the model class. That's the only bit I need. I import something known as a canvas grid. That's what I'm going to use because I've got a grid-based environment, so I'm going to use that to draw my grid. And I'm going to import something known as Jupyter Viz, which basically contains visualization to visualize a model in a Jupyter environment. Basically, the first thing we do is we write this thing known as a portrayal function in MESA. Basically, a portrayal function just says, this is how I want you to draw this thing. Okay, so here, this is a portrayal function that I created to define how I want it to draw an agent. So I pass in an agent, and I say, whenever you get given an agent, this is how I want you to draw them. I want you to draw them with this size, with this color, but I want you to change the color if they love HSMA. So the agents will be gray by default, but then if they love HSMA, they'll be red. So we should see then basically grey and red HSMAs, and as more love HSMA, we'll see more red, as fewer love HSMAs, we'll see more grey, etc. And then it returns something known as a portrayal dictionary, which is just a dictionary which contains the key as being the name of the attribute, and then the value as being the variable where we set it up here. That's all it is, okay. We also set up a visualization of the grid, which, as I said, is something known as a canvas grid. We pass into that our portrayal functions. So we've just written that. That's the agent portrayal. That's how we want it to draw its agents. And then various parameters defining the size of it. So we want that to be a 10 by 10 grid. And I want it to display at a size of 500 by 500 pixels. Okay. Then we set up a parameters dictionary, model parameters dictionary. This will basically set up, pass over to the model the various parameter values that we want. Okay, so in this dictionary, the key will be the name of the variable exactly as we defined it back in the models constructor. Okay, so where we had, for example, the number of agents, we call that n. That's what we're going to call it here. Okay, so all of those parameters, we need to give them the same name in the key. That'll be the same name as whatever we called it in the model class. And the value will be the value we want to pass over to the model when it runs. Okay, so you'll recall when we set up the constructor for our persuasion model, we said when we create a new model, we'll tell you the number of agents, we'll tell you the width of the environment in cells, we'll tell you the height of the environment in cells, we'll tell you the probability that an agent initially loves HSMA and the maximum level of persuasiveness of any agent. And those last two things you need to it will need to give to the agents when it creates those things in turn. Now, because we're using this visualization engine bit, we can actually have any of these things as being user definable, and we can use user interface elements like sliders in order to do that. So I'm not going to go through this code in detail, but I'll just quickly show you, if I can move this out of the way, the love-hate server. So this, let me get rid of this, sorry. Pull it down a bit. This, have a look at it in your groups, but this is basically the model parameters dictionary, and it's a dictionary of dictionaries. Okay, so you've got an outer dictionary where the key for each one is the variable name that is used in the model class. So n, initial love prob, you will recognize all these things, and the value is against that key is whatever value we want to pass across. So in the case of width and height, we don't want that to be user settable in this case. So I'm just going to pass over a value of 10. So we just write simply 10. But if we do want the value to be chosen by the user, then we pass the value of against that key as a dictionary, another dictionary itself. And that dictionary contains the type of interface element we want to use. So slider int is basically a slider that contains integer values, slider float, floating point values, etc. The default value, the label we want next to that slider, the minimum value that slider can go down to, the maximum value it can go up to, and the increment. And you do that for each one. And that's basically all it does. So have a look at that in your groups. But basically, you can set up these interface elements really easily. It's just, I say really easily, it's just a little bit awkward because you have to think of a dictionary of dictionaries. It can look a bit messy. So that's why I've kind of structured it in that way. Once you've done all that, you can basically then just create what's known as a page. So you create a new Jupyter visualization, which is the one we imported. You pass in the model that we imported. That's the model we wanted to run. We pass it the model parameters dictionary that we just set up. We tell it the measures that we wanted to track. So MESA will automatically track any data collectors that we specify. Remember, we set up 2 of those. And we gave them these values: total loving HSMA, total hating HSMA, whatever those strings were that we set up in the model constructor, that's what we need to call them here. And how we want our agents drawn, the portrayer function, which I just called agent portrayal. We set up the page, and then we just say page. This will work as long as you are in a Jupyter environment. So either Jupyter a notebook or Colab, or as most of you will be doing, using VS Code with a .py file, but running it in an interactive window. So you must run this in interactive mode, otherwise it will not work. Okay, it has to be in a Jupyter environment. So basically what this is doing, we'll run the server file. The server will bring up an interface. The users will select various parameters. The server will then in turn run the model. The model will create a new instance of the model. The model will then start up the scheduler, which in turn will start up each agent, which in turn will run its step method and do all its behavior. So there's this kind of sequence, this chain reaction that happens. And indeed, let's have a look at it. We've been building up to this for so long, so let me just move this out of the way. Make sure I'm running the right one. I am. You'll need to, when you do this, don't forget you'll need to be in your ABS environment that's supplied. So make sure you do that. But then if we run this code, hopefully you need to run the server file. This will pop up. So here is our just a random allocation of some agents. This is going to track the total loving HSMA and the total hating HSMA over time. And you see these are the sliders that I set up. So I said that the user can choose how many agents at the start, the probability that they love HSMA at the start, and their maximum persuasiveness. So if I run this model by clicking play, you can watch it play out, and you can watch those agents moving around. And remember, the grey ones hate HSMA, and the red ones love HSMA. It's not looking good here for those that love HSMA. Although there's a bit of a comeback coming here. We can monitor those things over time. You can do, and you'll see later, you can do more fancy things with this, but literally out of the box, you can just by saying, I want these outcome measures to track those 2 data collectors, then it'll automatically just set up some graphs without you having to do anything. But you can do your own stuff as well, which we'll see later. But you can see here, unfortunately, the haters have won. There are no lovers of HSMA left, and so therefore we've reached that steady state there. Okay, right. What I'm going to do now, I'm going to stop. No, I'm not going to stop sharing. I have stopped sharing. I will share again because we're going to go on to the exercise. Although you're going to take a break first. So here's what I want you to do. First of all, take a break and don't think about agent-based simulation for 10 minutes. But then I want you to work in your groups for about an hour and a half, okay? And your task is to do the following. Remember, you're going to need to use the ABS environment that we supplied for this. First thing I want you to do is have a look back over the code. So the two code files that we were just talking through there. So that's just to clarify, to make this perfectly clear, because you've been given various ones. That's the HSMA love-hate server. And, oh, sorry. Zoom keeps getting in the way. I know you probably can't see this, but it's really annoying. And HSMA love-hate model. Those are the two files that when you're looking at this stage. Don't look at the other one, which is the batch runner. We'll come back to that this afternoon. That will confuse you. So just look at love-hate model and love-hate server. Okay. So go back through the code that we talked through. Particularly have a look at the server file, which we obviously went through quite quickly. So you may want to have a bit more of a look at that. Have somebody sharing the screen, make sure everybody and talk through it, make sure everybody understands how everything works. Then once you've done that, I want you to, as a group, I want you to adapt this model. So first of all, take a copy of it. So take a copy of those two files, keep them safe. So you've got the original if you need it. But then I want you to make some adaptations to the model. Okay. So at the moment, this version of the model that we've developed has only concepts of love and hate. People either love HSMA or they hate HSMA, and there's nothing in between. So I want you to adapt the model in the following ways. I want you to set it up so that each HSMA has a love score instead, which kind of represents how fond they are of HSMA. But here's the kicker. I'm not going to tell you how to do that. It's entirely up to you how you do it. And I expect each group will come up with a slightly different solution. And I'm doing this deliberately, okay? Because this is what agent-based simulation is about. There is a far more freedom and flexibility, and that can be tricky because it's not quite so ordered and structured as some of the other approaches. But it's really important you think creatively about this kind of stuff. So there is a proposed solution that I will share after the session, which does this stuff in the way that I chose to do it. But it may look totally different to the way you choose to do it, and that's okay. Somehow, I just want you to implement this idea that each HSMAs have a score rather than just a binary feeling about HSMA. I also want you to capture somehow that HSMAs have who have stronger emotions. So if they love HSMA more, they hate HSMA more, they are more likely to be persuasive than those whose opinions are not as strong. So those whose opinions are stronger will be more persuasive. Again, entirely up to you how you decide to do that. How are you going to model that aspect? I'm just telling you what I want as the stakeholder. I want you to model that in some way. How are you going to do that? Okay. I want you to also make the probability that an HSMA moves on any given time step, which at the moment is just a coin toss, 50-50. I want you to make that a probability that gets fed into the model and which can be set by the user. So the user can define basically how likely it is an agent will move. In other words, that's kind of a proxy for our model. That's kind of like saying how much are our agents, our HSMAs, how much are they sort of moving around and engaging on Slack? That's kind of a proxy for that. And the other thing I want you to do is to update your visualization of your agents and also your outcome metrics to better represent this new logic of the model. Okay, because at the moment you've basically got a visualization that tracks people that love HSMA and people that hate HSMA, and your agents are coloured grey or red to reflect that. That's it. But that's not going to make sense in this new version of the model. So you need to think about how you change the visualization. And again, how you do it, entirely up to you. How you choose, how might you best decide to visualize this new information? Okay, so there's a lot of model design stuff going on here, and that's crucial for an agent-based simulation more than any other approach that we teach you. Once you've done that and you've made your created your new version of the model, I want you to run the model, see what behaviours you see emerging, and if you happen to get through all that, then as a group, I want you to make some additional adaptations or extensions to do anything you like. So, let your creativity run free. It's more important to give you the time to do this. So I'm going to earmark about our, probably will come back. I think originally I was going to get you to kind of present each group to present. I think what we'll probably do is just get you to put your models into your Slack groups. So we'll probably run till about 25 past 12. So give you a 10-minute break and then an hour and a half. That might change, so just keep an eye out on messages, etc. But probably 25 past 12. We'll just come back briefly for lunch, and then we'll move through. But we'll be floating around. If you need any help, don't free your minds. That's what you need to do. Free your minds. Don't get stuck in this is how you have to do it in an agent basically. Think about how you might approach this. This is a really good practice for not only agent-based simulation, but also creative coding, object-oriented programming, all of these skills that you're going to need, regardless of what project you end up doing. Okay, I will stop sharing and I'll open up the groups, but do go and take a 10-minute break first. Hi everyone, welcome back. I just wanted to pull you back for briefly for 5 minutes before lunch. I managed to get around to most of the rooms, I think. Really interesting to see how you were taking to agent-based simulation. I think it'd probably be fair to say that more of you are enjoying agent-based simulation than system dynamics. That's really nice to see. You all kind of got spent most of your time, as I expected, trying to work out how you were going to kind of implement this logic of a score and a different sort of a definition of what persuasion meant, and this this kind of different logic. And I did this deliberately because a lot of if you're building an agent-based simulation, a lot of your effort is going to be. I mean, this holds true for any model that you do. So when you come to your projects, a lot of what you're going to be trying to understand is how you're going to design it, your conceptual modeling process, how you're going to translate this real-world system into essentially a mathematical model. But with agent-based simulation, kind of, that you've got so much that you can do, but B, you are typically trying to capture mathematically some sort of representation of human behavior. And obviously that gives you a lot more scope for how you're going to be thinking about this kind of stuff. And so it is no surprise to me that most of you spent a lot of time trying to work that out, how you're going to do this for this relatively sort of simple example, because that's exactly the kind of thing you need to think about for an agent-based simulation. So I deliberately did this for you. And it's a really important skill whenever you're designing models. So hopefully you've posted your models in your Slack channels. If you haven't, please do so. Can I also ask you to one of you to just give just to make it easier for Sammy looking over these, just give a very brief, sort of couple sentences description of how you did it. So how you how you came up with this idea of having a love score and how that people would influence each other. So just describe the logic. And also, if you did get to the stage where you made any sort of additional tweaks or you found any insights, pop that in there as well. That'll just help when Sammy comes to look at that. What I'm just going to do, just for a couple minutes, just before we break for lunch, I'm just going to very quickly show you my solution. And again, it is not... particularly with something like this is not the right answer. You may come up with a much more interesting way of doing it, but I'm going to show you how I did it, and then I'm just going to talk very, very quickly, and then I'll post that. So if you want to have a look, I'll post it on Slack so you can have a look if you want to before this afternoon's session. It may help you when you come to this afternoon's exercise think through how you're going to design some of this stuff. So let me just share my screen and get over to the code. Okay, so again, you can do this in multiple ways. So I had this idea that basically I'd have a score. But let me just zoom in a bit. So I'd have a score between 0 and 1. I think a lot of you got to that point, so that essentially just randomly allocate a score between 0 and 1. I still had a persuasiveness, but my persuasiveness now didn't have a maximum. And persuasiveness, rather than representing a kind of probability that you will persuade someone, represents more a level of persuasiveness. So it's kind of a little bit different to how we had it in the original. So I've just set it to 0.2 for any agent by default. I don't think any of you had a problem with the probability of moving stuff. That was all fairly straightforward. What I really want to focus on is how they would now persuade others, given you've got kind of this score-based measure rather than just a sort of binary I love or hate HSMA. So the way I did it was basically I looked when I went to talk when an agent went to talk with someone, looked at the cellmates the same as before. If there are other people there, what it would first do is try and determine what my persuasiveness will be at this point in time, because that will change, because my persuasiveness is dependent on how strongly I feel either in one direction or another. So I just had a simple if statement here, and basically said, look, my persuasiveness, I'm going to set it to a value of 1, sort of maximum persuasiveness. If I've got a very low or a very high love score, 0.8 if it's kind of pretty low or pretty high, etc. So I had these different levels of persuasiveness, 5 different sort of tiers depending on my love score and how close to 0 or 1 those things were. And then I would look at the love score of the other person, the person I'm trying to persuade, and if they basically what I would then do is either if they've got a higher score, I'd bring them down closer to mine, or if they've got a lower score, I would bring them up closer to mine. If they've got the same score, then essentially do nothing. But the way in which I decided to do that was to say, okay, well, I'll take the difference. So if the other agent's got a higher score, they love HSMA more than I do, I'll look at the difference in the scores, and then basically I'll bring them down closer to me, and the amount I'll bring their score down closer to me, I've taken as the difference, whatever the difference is, multiplied by the persuasiveness. So if by my persuasiveness. So if I'm a very persuasive person because I feel I either hate HSMA very strongly or love HSMA very strongly, then I will bring them down by the full amount of the difference. I'll bring them all the way down to me. But if I'm somewhere in the middle, where I quite like HSMA, or I don't really like HSMA, then the difference would be multiplied by 0.6. So you kind of get a fraction of that difference. So they're gradually sort of moved down closer to me, but I haven't persuaded them all the way. So that's quite a blunt instrument way of doing it. And the same if their score is lower, just with the calculation reversed, basically. And indeed, if you run that version of the model, what you'd see if you're modeling the behavior in that way, as you would probably expect, is that people. I've run the wrong file, haven't I? I need the server, which is that one. Let's close that down. By the way, just while I'm doing this, hopefully you all saw my message, but I know a number of you are having problems thinking, well, everything looks like it's working, but it's not. With MESA, with the server visualization, sometimes you need to restart your kernel for it to kick back in. So be aware if you're looking at it thinking, well, I don't understand why this isn't working. So it's a bit weird in the way it does it. That only applies to the server. When we come to the stuff this afternoon where we're not using the server, you shouldn't get that issue. But just be aware of that. So you can see here I've also coloured my agents differently. So I think the stronger, the more they love HSMA, they get sort of oranges and reds, and hate is kind of greys going on through browns, etc. And what we'll see if we run that, and however you do this, as I'm tracking the mean love score there, as you would gradually expect, people kind of converge until they're all kind of feeling the same kind of thing. So here we end up, and you can see this tiny little movement still happening, but it's gradually settling down, so that people end up feeling that they quite like HSMA in this particular example. Because of course everybody's kind of pulling in each other person a little bit closer to them, so everybody's just ends up kind of converging. And you'll see with that approach to the modelling, that will happen each time. They'll converge to a different point. So hopefully, I mean that, as I say, that's just one way of approaching it. And I've seen some really interesting ways in which you all approached it. If you were doing this as a real world model, this is really where you want to try and be speaking to your stakeholders and understanding. And as we talked about last week, very often this may well be, depending on what you're doing, if you're modeling patient behavior, you may well want to be speaking to patients and getting involved with patient groups and talking to them about why they behave in certain ways, why they might choose to do certain things, and to try and convert those things into mathematical rules that kind of approximate that behavior. That's essentially what we're doing here. So essentially, I've created a version of this where I've spoken to the people and they said, well, if I feel very strongly, I always manage to persuade them to my argument. But if I'm a bit less persuasive, then they'll see my point and maybe change their opinion a little bit, but not quite as much. That's essentially what I've captured with my mathematics. Okay, so I'll post that in the class tannoy, so you can all have a look at that if you like over lunch. But go and have a break now. We'll resume at 1:30, and then we're going to talk a little bit this afternoon about batch running, which is a different way to set up our models. And then you're going to have a go at something really creative for most of the afternoon. So go and have a break now. Go and enjoy some lunch, stretch your legs, and I'll see you at 1:30. Bye, everyone. everyone, welcome back from lunch. Hope you managed to get a bit of a time away from the keyboard over lunch, and we're going to plough on this afternoon with a little bit more of MESA initially, and then you're going to have a bit of a play around with a larger scale exercise that I'm going to give you to try and really pin down some of this creative decision making and conceptual modelling that you need to think about whenever you're designing and developing an agent-based simulation, and have a chance to come up with something hopefully really creative. So obviously this morning we covered the basics of MESA. We looked at the kind of basic structure of using a MESA as our framework for building an agent-based simulation. This idea that we have a class for each agent, a class or each agent type, a class for a model, and some data collector functions, and that represents kind of our model file. And then what we did this morning, obviously, was to have this kind of separate server visualization engine, which basically would spin up a server on your local machine and run a visualization, so you could sort of watch the model pan out and watch your little agent sort of move around the environment. What we're going to touch on next is obviously that's a really useful thing to do, but of course if you were doing this in earnest, you may also want to, you don't want to necessarily sit there and watch a visualization every time you run your model. You may be trying to get results out of it as well. So you might also want to run your model in a slightly different way. And MESA comes with a fantastic, as well as the fantastic visualization stuff, it also comes with some really nice ways in which you can try out different scenarios in your model in batch without you having to do a lot of legwork. So I'm going to talk you through briefly some of that stuff now. So we've looked this morning, obviously, at, basically building an agent-based simulation with a live visualization component. We're watching that model unfold live before our eyes. But of course, we also know, because we are good modelers and we remember our discrete event simulation training, and we forget our system dynamics training, because that's usually the best thing to do, that typically when we've got a stochastic model, and this is an example of a stochastic model, we've got elements of randomness in it, unlike our system dynamics models, that we shouldn't just run a model once and draw conclusions and insights from that. In fact, if we've got a stochastic model, we should run our model multiple times, and we should explore our results over kind of batches of runs. And we can do that just as with a discrete event simulation. We can do that too with an agent-based simulation. And MESA allows us to do this really easily using something known as a batch run. And the batch run's also got these really cool features that allow us to try out these different scenarios, these different combinations of parameter values, and it will do all the hard work for us. So it's a really nice feature of MESA. So to run the model in batch run, we only need the model file. We don't need that server one. In reality, if you're building an agent-based simulation, you probably want to do both. You probably, initially as you're building the model, want that visualization thing there, and that's a really nice way of engaging with your stakeholders, to show them the model running. And when you come to then get some results out of the model, you would then turn to the batch run. But we only need the model file. We don't need that server file for just doing a batch run. So what we're going to do, we're going to go back to the original model, the one I showed you this morning, the one with the kind of binary love and hate, and there's a chance that you'll, anybody that talks to someone, that they'll persuade them, if they think differently, that they'll persuade them round to their binary love or hate. And we're just going to adapt that model very slightly, just to allow it to run batches of simulation runs. So again, this example is provided in the repository for this session. This one's in the HSMA love-hate model batch runner folder, and you'll see a file called HSMA love-hate brmodel.py. Basically, this is most of the stuff that we're adding to this is going to be right at the end of that code file. So most of the stuff in that file is going to be exactly the same as the one I showed you this morning. There is a slight difference. We need to import. There's a couple of extra things we want to import. Neither of these are essential for doing a batch run, by the way. Except I would say that they are hugely useful for reasons that I will demonstrate. So we're going to import pandas, our good old friend pandas as PD, so we can do some analysis. We're also going to import matplotlib as well to allow us to generate some of our own graphs, because we won't get those sort of nice visualization graphs if we're not using the server. So we're going to do it manually instead. Incidentally, something I only touched on but didn't quite mention, I will link in a little bit to the documentation and the tutorial that you can read on MESA's own website. In the visualization stuff, they also show you how you can add your own graphs to those live server visualizations as well. So you can do have a look at that if you're interested. Okay, so apart from those import statements, everything else we're going to add for doing a batch run is going to be to the end of the file. So we've just added in a couple of extra imports at the start. Everything else will be exactly the same. It's just we're going to add some stuff onto the end of our model file. That's all we're going to do. So the first thing we need to do is we have to set up our model parameters as a dictionary. Now, we did that before when we had our server file. But what we were doing with the server file was we set up the parameters in a dictionary, and some of them had themselves dictionary values within it, where we wanted the user to, be able to adjust certain things. And then the server basically then kick-started the model and passed over the parameters dictionary. Obviously, we're not using the server now, so we need to set up the parameters dictionary ourselves. What we're also going to do is specify if we want it to look at different combinations of parameter values, different scenarios, if you like. So we're going to pass in some parameter values that are fixed, and we're going to pass in some parameter values that are in lists or some other iterable object that Python can go through. And what will happen is MESA will go through and it will test every combination that we've potentially specified. Now, I must emphasize at this point, be extremely careful about doing this. It is very so agent-based simulation is quite a computationally expensive simulation modeling method, because you're modeling lots and lots of separate agents. Now, obviously, the example I showed you this morning was fairly lightweight, but you can get into some quite complex modeling, and you were only using up to 100 agents, and most of you just stick around sort of 20. You can end up with an agent-based simulation quite easily that has very complex behaviors and modeling thousands of agents. That takes a lot of computational resource. If you then need to model lots and lots of different combinations, you will very quickly find that you get an exponential increase in the number of combinations that you are trying. And I will demonstrate this a little bit as we move through. So here's my parameters dictionary that I've added. So it's just a simple dictionary. I've just called it params. And you can see each key value is basically the name of the parameter. This needs to match the thing you're passing into the model class, what's set up in the constructor. And the value is the value I want to do. So width and height, I'm just setting as 10. So I just want the width and the height to be so 10 cells wide, 10 cells high in my environment. But for n, remember, n is the number of agents within our model. I'm not going to pass a fixed value. I'm going to pass a range of values. And what MESA will do, it will automatically work out, oh, okay, you want me to test all of these things. Okay, so I'm passing in this range here, range 5, 1055. Now, if you think back to many moons ago when I told you about ranges, when we were first learning Python, we said we can use this triple argument version of a range to specify. So the first value here will be the value you start from. The second value is the value you go up to but do not include. And the third value is the increment. So this says I want agents from 5 up to but not including 105 in steps of 5. So what that will actually give you is The combinations 5, 10, 15, etc., all the way up to 100. It won't, when it then gets to 105, it won't do that one. So that's 20 different combinations. Okay, so every value of multiple of 5, basically up to 100. No point in having a 0 agent model, it's pretty boring. In fact, I don't even know if it works. It might work. I don't know. There's no point testing it. It's completely pointless. So that MESA has already said, okay, right, I now need to try 20 different combinations of this model. As well as that, my initial love probability, which remember in the simpler model is just the probability that they love HSMA versus hating it. I want you to try, I'm going to pass in a list here, and I want to specify these values. These are the values I want tested. So I've put 0.25, 0.5, and 0.75. Okay, so that's another 3 combinations. And then the persuasiveness, same thing here. I'm going to pass in 0.5, 0.75, sorry, the maximum persuasiveness, I should say, 0.5, 0.75, and 1. So that's another 3 combinations. So just without anything else, MESA is going to test 180 different combinations of this model. Okay, all I've asked it to do is try these different combinations of numbers of agents, initial love probability, and the maximum persuasiveness. So basically, it's going to go through each combination of those things. So 5 agents with 0.25 initial love, 0.5 persuasiveness, and then 5 agents with 0.5 initial love and 0.5 persuasiveness, and then 5 agents with etc. etc. It's going to go through every possible combination, and there are 180 of those. So already you're starting to see if this is a more complex model, this might get a little bit out of hand if you start going a bit too ambitious with this. So that sets up our parameters dictionary. The next thing we're going to do is create a MESA batch run. Okay, and this is a construct that we can use from MESA that allows us to do all this. And so what we're going to specify when we fire up a batch run, or create a batch run, is we're going to specify the model that we want to batch run. That's just the name of whatever we've called our model class. So here it's a persuasion model. We're going to provide it our parameters dictionary. That's the thing we just wrote in the previous slide. We called it params. So I said parameters equal params. We also need to set up the number of iterations for each scenario. So remember, when we do discrete event simulation, we have a parameter combination, but we don't just run that parameter combination once. We run it multiple times, and then we can take sort of average results over that set of runs. So we're basically a day in the life of our GP surgery where we've got 1 receptionist, 2 nurses, and 4 doctors. Let's run that 5 times, 10 times, 100 times. Now let's try it with 2 receptionists, 2 nurses, etc. Let's run that 100 times, whatever it may be. So the iterations is the number of times it repeats the same scenario, so that we can, because it's a stochastic model, because we need to repeat and just make sure we didn't just get a run of good or bad luck. Then we've got the maximum number of steps, which is basically the amount of time that the model will run for. Excuse me. So number of time steps in the model. So I've just set it up to 250, so it'll run for 250 time steps. As with most modelling approaches, what a time step represents is entirely up to you. Just make sure you're consistent about that. Number of processes here, it basically refers to the number of processes that you can use. You can use this in order to use parallel processing on your computer, except if you're using Windows, which 99% of you are. So you can, if you're using a Mac or Linux, you can feel smug here because you can type in the number of, up to the number of processors you've got. I don't know what happens if you put more. I'm guessing it's clever and it maxes out. But you can specify how many concurrent operations you want going on across your processors. If you're using Windows, there is a way around it. It's very, very complicated. Don't bother. Just stick it at 1. Okay, so another joyous reason to use Windows for data science. But there we are. If you're using a Unix-based OS, you do get an advantage here, and that is quite significant potentially if you're running a particularly complex model and/or lots of combinations. Then we have the data collection period. This represents the amount of time, how often basically we want MESA to record the data, so kind of the period of the data collection. So that's our data collector. How often do we want data collector to collect? or data collectors, we may have more than one, and that's given in time steps. If we specify it as -1, which is what I've done here, then basically it will only take data once the simulation's finished. So it'll look at what's it like at the end of that 250 time steps. But you can, if you so choose, if you put 1 there instead of -1, it will record data from every single time step of every single run of every single combination that you specify. And that might be what you want, in which case you can do that. Or you can say, look, just give me results every 10 time steps or whatever. I've just set it for simplicity, just to -1 here. So we'll just get the final results. What happened at the end after 250. And obviously, what you do there is going to depend on what you're building this model for and what you want to get out. And then the last one here, display progress, I've put that to true. It just determines whether or not to display a progress bar. I would advise doing that so you know how far through it is, because these things can take a little while. So just be aware of that. So this sets up a batch run in the way we specified, and it will store the results in a dictionary. So we need to assign that into a variable name. That will become a dictionary. I just call mine results, so that when we run that batch run, it'll all be put in a dictionary. I have to say, I don't think that's the best. That's one thing I don't like about MESA. I don't know why it puts it in a dictionary. That's not how I would do it. Particularly given you've got a thing called pandas, and particularly given that it installs pandas as a dependency, so it does use it, but doesn't here, which is odd. Don't worry, I'm going to show you how you just very easily convert it into a pandas data frame, and it's very, very easy. But just know by default it stores it as a dictionary. So we said that we've got 180 different combinations of 180 different scenarios, i.e. 180 combinations of parameter values we wanted to test. On top of that, each of those 180 combinations is also going to be run 5 times, because we need it to repeat. And actually, that's a fairly low number, but I've kept it low to make this manageable. So that takes us up to 900 total simulation runs. Okay, 180 parameter combinations, and each of those repeated 5 times will take us to 900 different. So already this is escalating, and at 250 time steps per run. That means in total, to run all of these things, even with this fairly constrained combination that I've done here, it's going to essentially run 225,000 time steps. Okay, so that hopefully just sort of flags up that you can get into a bit of a mess quite quickly if you're not careful. So this should be doable on your machines. It's fairly quick on mine. It's going to be probably a little bit slow on most of yours, but it should be runnable. At the very least. But just be warned, because you can see how you could easily, just even adding in a couple more things down here would have had another exponential increase. You'd have had an order of magnitude more combinations and time steps, etc. to run. So be aware of that. In fact, so much so that I remember years ago, Mike had just bought, or had bought from a brand new, very high-powered computer for the office, and he allowed me to have a dial into it and have a play with it. He said, you can chuck anything at this, and I brought it down. I brought the entire computer down just by accidentally having too many combinations of an agent-based simulation. It was still trying to allocate enough memory in order to write the table of results. So it didn't even get to running the simulation. So just be aware of that. This is going to be memory hungry and processor hungry. So just be careful. Start small and gradually build up. Don't go thinking, oh, I'll just try everything. That's the temptation, because of course it does it all for you. It's very easy. I could chuck in millions more combinations in the a flick of an eyelid there, but just be very careful about that. Unless you've got a very, very fast computer or you're very patient. Okay, so we've set up our parameters dictionary. We set up the batch run. That's actually all we need to do in order to run the batch run of the model. But as I mentioned, the batch run will spit out the results in a dictionary, which isn't probably the best thing if we want to analyze them. So we're going to convert them to a data frame. So I've done that here very easily. I mean, this is why we love pandas. You've got a dictionary called results. No problem, you want that as a data frame. That's easy. PD.dataframe, pass in the dictionary. There you go, you've now got that as a data frame. Perfect. And then you've got much easier to analyze from that. What I've also done here as well is just a little bit of further analysis. This is just an example of something you might want to do with these results, but obviously this is going to entirely depend on what you want to do with your results. The only key things you have to do are those first two steps, and I would argue put it in a data frame. What you do after that point is entirely up to you. Okay, so this is just an example of what I might want to do here. Here, what I've done is I've looked at the outcome of interest, which I've decided is the number of HSMAs who love HSMA at the end of a run for each scenario. And what I'm doing is I'm taking means across the runs for each scenario. So remember, each scenario is run 5 times. So this bit of code here basically will find each of those scenarios in the data frame. So you've got a load of nested for loops there, because it's basically picking out, okay, I want the scenario where there's 5 agents and the love probability was 0.25 and the maximum persuasion was 0.5. Give me those 5 runs. That's what this is doing here, the filtering of the data frame. And then basically what it does is it takes the mean of my total loving HSMA, takes that for those 5 runs, whacks it in a temporary data frame, and then I'm whacking that onto this big data frame that I'm building called the scenario data frame. So it keeps looping through, and then I'll end up with a slightly more refined data frame, because the results data frame will just have everything. It'll have all 900 different runs. The scenario data frame will have 180 entries, i.e. one for each scenario, each parameter combination we test, that will have the average result. So if I run this combination of agents, love probability, and persuasion 5 times, what was the average? Okay, which is probably... So the reason I've done this is to show you an example of something that's probably the sort of thing you'd want to do, and you can do that fairly easily with pandas. So that's what this is doing. So hopefully that's a useful piece of code if you decide to do that. We might also, of course, want to plot our data, and again, this is entirely up to you. But I've added a bit of code into the code file, which basically where we can see that I've plotted some of these results that have come out. And here I've plotted basically the mean number of those who love mean number of HSMAs loving HSMA by the end of the run. For various number of agents, so that's on the x-axis here, so that this is an increasing number of HSMAs for different scenarios where they have different different percentages of HSMAs who initially love the program. So the blue line represents where only a quarter of them love it at the start. Green line is where half of them love it at the start, and the red line is where 75% of them love it at the start, and this is all for where the maximum persuasiveness is 100%. So I've got multiple different dimensions here, and if I just switch over to the code, if I can bring up the right one, that one. Let me just scroll down to the right place. So I mean, I'll let you have a look at this yourself, but this is just standard matplotlib stuff. So I'm just picking out because I've taken the scenario, built up this scenario data frame. I can just grab the entries I need. So where the initial love probability is 0.25, the persuasiveness max is 1. That will be my Y data, etc. So that's where I pull out my data, and then it's just a simple plot, as you've seen many times in Matplotlib. So I'll let you look at that in your leisure. But again, it's another way in which I can model or I can explore my results. So let me just run that code just so you can see what happens. So obviously this time we haven't got a server, so it's just going to run in batch. So this is running 900 different runs of the model. You can see we've got this progress bar. It's gradually sort of counting up. Bear in mind, I've got a pretty quick computer, so this is going to take a little bit longer on yours if you run this. So just be aware of that. But it's trying those 900 different combinations. And then out to the other side, it will spit out the results, which are converted into a data frame, and it should come out with a nice graph. We're nearly there. 96, 97. Here we go. It should pop up any second. There we are. So that's the graph. So that was what I've just shown you a moment ago. If we have a look at the data frames, if I go into, let me just bring this up, go into Jupyter, and of course I can explore my results. So the results DF, this is, so in fact, let me open up this first. So if we hadn't converted it to a data frame, this is how it comes out, like that. Okay, those are your results. Now, hopefully, you can see why you probably want to put this in a data frame, which is what we did. And oh, sorry, it's Zoom. I have to keep closing this. So the results data frame, what we converted that dictionary into, if I click on this here, that looks like this. So you can see here we've got, let me just close that down. So you've got each run ID, the number of the iteration, the step number, which will always be 250 because we told it only to collect data at the end of the run. Remember, I could have done that so it was every step if I wanted to in that, and then we'd have had a massive data frame. Width and height, obviously those things didn't change. You may, in fact, if you're doing this analysis, you may want to get rid of stuff that doesn't change, drop it from your columns in your data frame. But then over here, we can see that there is the number of agents, different numbers of agents with different initial love probabilities and different persuasiveness, and we can see the total loving HSMA for each run of that combination at the end, and the total loving, total hating HSMA 2. And I've just closed that down, haven't I? That interactive window, sorry. Let me just very quickly run that again. Fortunately, it's fairly quick on mine. So that's the kind of raw, it's a slightly more readable, a lot more readable version of the horrible dictionary that it spits out, but it is still all of the results from every single run. So there's 900 different entries. But of course, what we do here in this bit is to say, okay, well, I want to look at the averages for each different scenario, each parameter combination that I've tested. And once this runs, I will show you that. Nearly there. And there we go. Okay, so if I now click on Jupyter and scenario data frame, that's the data frame I built there. And you can see if we scroll across, so we've still got this same stuff here. But where's my scroll bar gone? That's really annoying. Where is that? Why can't I scroll across? Can I do that? Oh no, sorry, it is. It's all on one. Sorry, I'm getting confused. This is because this is the data frame I've built up. So I've only included stuff that I'm interested in. So I've dropped. I don't need to know about width and height or the run number and things like that. So this will only have 180 entries. And each of those entries is going to represent one of those distinct scenarios. So you can see that here. This one had 5 agents, 25% probability of initial love, 50% maximum persuasiveness. This one had 5 agents, 25% initial love, but 75% maximum persuasiveness. So these are your 180 different scenarios, and for each one, I've got against that the average number of people who, by the end, loved HSMA. Okay, so this is probably the kind of analysis you would want to do if you were doing your own agent-based simulation. Just well, actually, no. Hang on, let me just go in there. Sammy, are there any questions that have cropped up about anything that I've gone over there?
So nothing too much. Let me just double check. So the one I couldn't answer was, well, around does it store the results in memory? Can you tell MESA to store the results to the hard drive instead? And I think this was around when you were talking about, exceeding the capacity of the memory to store the results. My initial thought from having a quick look at the documentation, I don't think you can tell it to directly store it to the hard drive, but you could get a bit creative with your use of loops and writing things out throughout to make sure that you don't exceed the capacity. But I don't know if you've got anything you'd like to add to that.
Yeah, I'd just be I mean, if you're exceeding your memory capacity, you've probably gone too much for your computer anyway. So if it can draw even if it could draw the table, then it's gonna struggle to actually run all this. So yeah, no, it needs to run in memory. A shorter view trying to reverse engineer. I mean, you could. It's open source. You could rewrite Mesa's package. That is actually a thing you could do. But yeah, no, I think I wouldn't go doing that. I would focus on just trying to, as you say, have more controlled batches of batches. I think would probably be a better solution.
Cool. And the only other one to highlight is so Dom was having a go with what happens regarding the number of processors if you're using, or the number of processors if you're using Windows subsystem for Linux. And it looks from, does that kind of go down the Windows route, or does that work as if it would work in Linux? It seems like it might be the latter. But
Yeah, sure.
yeah, that's so fingers crossed that's all good if you're on WSL.
Yeah, I think so. Obviously, I've not tested it, but it should pick up as long as if your Python environment is through Unix. Essentially, it's running in a Unix virtual machine. So it should the instructions that it's giving to process should be Unix instructions, and it will be acting as though it's a Unix. The virtual machine is then worrying about how you translate that into Windows instructions to then communicate to the processor. So yeah, no, it should be absolutely fine, because you can even do stuff around accessing. Well, you can't do GPUs, but you can do um, stuff that interacts in a Unix way with your computer through a virtual machine. So yeah, that should be fine. That would make sense. Uh,
Perfect. And that's
Brilliant. Okay, so just obviously I mentioned this morning, but I just wanted to flag it up again because it is an important point. Um, the stuff that I've shown you so far, entirely sort of grid based, and people tend to, as I say, tend to get hung up on this idea of thinking about everything in a grid environment, or thinking, well, I can't do this as an agent based simulation because I can't work out what the grid is. You don't have to worry. The grid is actually optional, but there are things that you can even if you do want to represent it as a grid, that can help you think about that. And I did see a question, I think earlier this morning, asking about well, what if your agent, you don't want them just looking at the immediate neighborhood? That's okay. You can get them to move anywhere on the grid. You can it's just it's a list of cell references, and you can just tell it to move over there. It doesn't matter. Just for this, we're getting it to sort of move incrementally. But these are my sort of tips, really. If you are using a grid, well, your grid doesn't have to represent space. The physical space. What we did this morning with that model didn't represent space. It represented something more abstract. With effectively, it was people encountering each other on Slack, and we were just using a grid to kind of visualize that. But it could also be things like states of being. Your grid could represent this cell represents people in this state of being, this people that represents people in this state of being, etc. So it can be as abstract as you like. It doesn't have to be you move physically from here to here. You also need to remember you don't have to have your agents move. Some models don't have movement behaviors, and if they do move, that doesn't have to represent spatial movement either. So bear that in mind. And of course, also, you do not need a grid at all. Technically, you can build an agent-based simulation that is far more abstract and doesn't use a grid whatsoever. Now, just be aware that if you're using elements of MESA, it will expect a grid environment. So you'd have to be careful what you use and what you don't use. But hopefully, what I've shown you this morning is that obviously MESA gives you some nice shortcuts. But there's nothing really. The fundamental meat of your model, of an agent-based simulation model, is object here with attributes and methods interacting in some environment, and with it and each other. That's basically agent-based simulation, and you could do that just with pure object-oriented programming. Just bear in mind, if you're not using MESA, you have to do things like you have to replicate your scheduler. You need to work out. You'd have to tell each agent, you need to move now, or you need to do your thing and work out which order. But again, all that's fairly straightforward. So you can do it without MESA entirely. But yeah, don't let that constrain your thinking. An agent-based simulation, if you've got agents, things that you can think of agents that have their own kind of behaviors. And the thing you're interested in is, what if we chuck all those things in a box and then look down at that box and see what happens? That's an agent-based simulation. So bear that in mind. Don't let it constrain your kind of creative thinking. And as I mentioned, that my old B model didn't use a formal grid structure other than because I couldn't draw anything. I mean, my visualization was so terrible. I remember being interviewed by the BBC, our local BBC, at the time when I'd sort of come up with these conclusions. And he said, "Have you got any graphics to show from this model?" I said, "Oh, yes." And I showed him just his face. I've never seen somebody look so disgusted by a computer screen. I mean, it was basically some straight lines. The B was just a sort of oval with a yellow color, and then it would just change colors in these little circles. And he just looked at it incredulously and just, we can't use that. We cannot broadcast this on television. That's how bad my artistry was. So that's why I used a grid structure, because that was the only way I could get any form of visualization back then in the old days. So, but it was nothing to do with the mechanics of the simulation. Each B basically just had you had a sort of a table effectively of a matrix of fields, and they would select one of those things. So it's and those fields could have been anywhere on a landscape. You just had this concept of there's a travel time and all that kind of thing. As I say, if you want to read more about MESA, there's a huge amount more to read there. Their tutorial is actually much better than it used to be, so I'd probably recommend it. I only skim read the new version as I was panicking, rewriting this, thinking, why is my code not working? Realised I changed stuff. But it takes you through the example they use now is an agent-based economy model from econophysics. It's quite interesting, so do check that out, and you can have a look at. As I say, it's got. I've shown you a little bit of the visualization stuff, but you can. There's extra bits that you can sort of tweak and add your own little bells and whistles too. And indeed, you may want to do that because we now come to the main event of the day, exercise 2. You are now going to go into your groups. And you'll have, just under 2 hours now, so you have till about 4 o'clock. You are going to design and build your own agent-based simulation, and you've basically got 2 choices for how you approach that, and it's entirely up to your group which one you pick. Whichever one you pick, you're going to come back, you'll have sort of 2 to 3 minutes to present your model, and Sammy's going to award some PSG points, and there are potentially some really big points available for this. This is a big creative exercise, probably one of the more creative ones we've done since the hackathon. So this is a big exercise, lots of points available. So think creatively. This is a great opportunity to try out your model design skills. So first option is basically do whatever you like. Okay, create an agent-based simulation. It could be anything you want. You could pick the ABS that you designed in part 1. Remember last week you all came up with some designs for agent-based simulations, just carefree, thinking at least we have to code those things. Well, you may choose to do that now, but you don't have to. Or you could, of course, rip that off and think, oh, I'm not coding that. You may have had a better idea since anyway. So you can do whatever you like, basically. Whatever you do, think carefully about, what questions your model's going to answer, what your agents are representing, what behaviours they're going to have, how you're going to translate those behaviours into real-world human behaviour into rules of thumb. That's one of the hardest things to do. Whether your agent's going to learn, if so, how, what your environment is, how your agents will interact, if they will interact, motivations, goals, anything like that. All of that kind of stuff that we went over last week. That's option 1. Option 2 is you can do this. Option 2 is you are going to build an HSMA version of The Sims. Okay. Now you can design this however you like, but here are some potential ideas. These ideas are so just to be totally transparent. I originally had the idea that this was going to be the model that I would use to show you MESA. As I started coding it, I realised it's too much to introduce you to a new package. It would have been too expansive and overwhelming, and I'd have ended up saying, "Don't worry about that bit for a minute. Don't worry about that bit." But now you've got the basics of what a MESA structure looks like, potentially you might want to give this a go. So here was the idea that I had, but again, you could change this up if you wanted to. But in the HSMAs, HSMAs have 4 needs: to study, to eat, to sleep, and to socialise. And there are basically 3 areas in the HSMA house. You've got a dormitory in which you can sleep, the HSMA sleep, a classroom in which they study, and a canteen in which they eat. Now, HSMAs always choose one of those 3 activities to undertake: studying, eating, and sleeping. Those are the 3 things they can do. And each helps, each of those activities helps them to meet a corresponding need. So eating helps their eating need, sleeping helps their sleeping need, etc. In addition, they've also got this socialization need. And HSMAs who are either studying or eating will also meet their socialization need as well. And it turns out that people who are eating with others meet that need better than those who are studying with others. Need scores aren't currently being improved by an activity. So if you're currently eating, that's not helping your sleep or your study needs. So they will gradually decrease if you're not meeting those needs. And if any HSMA, any of the an HSMA's need scores reach 0, they leave the program. There's a limited number of beds in which they can sleep in the dormitory, and that can be adjusted by the user. An HSMA can't sleep unless there's a bed free, and if they need to sleep and they can't, they'll have to choose to do something else instead. We are going to assume, for simplicity, there is effectively unlimited capacity in the canteen and in the classroom, so they can always study and eat. Each HSMA decides what to do based on what they need the most at that time, with some level of randomness. If they choose to opt their socialization need, then obviously they could either eat or study, because both of those will help. And they will choose one of those depending on which one currently has the most participants. And each activity takes a amount of time that is determined when the HSMA decides to begin that activity. So I'm eating now, I'm going to eat for 10 minutes or whatever it may be, and that will be randomly determined within a kind of predefined range. You can build that however you like. You can change up those rules if you like, and I want you to use it to try and determine how many beds that myself and Sammy should install in our HSMA house dormitory to try and minimise HSMAs leaving the programme, whilst, you know, we don't like spending money either. So what's the fewest number of beds we can get away with to keep you lot happy is basically what I'm asking there, as well as any other behavioural insights that you might glean. So you're probably looking at that and thinking, I'm really glad, Dan, that you didn't give that to us this morning as a way of introducing MESA. And yes, I'm glad too. But if you fancy it, it's there. I came up with that idea, and if you want to run with it, it's entirely up to you. Or do whatever you like. Build on the model that you designed last week. Build something else. Entirely up to you. But you're going to come back at about 4, maybe just after, and you are going to each group present their models for big points. Okay. Any questions that have come up about the exercise?
No, nothing on the exercise.
Excellent. Okay, cool. In which case, I will stop sharing. I will open up breakout rooms and I'll float around. So have a chat in your groups first about what you want to do and how you want to do it. Obviously, don't forget, obviously this is running for most of the remainder of the afternoon now, so don't forget to take a break in your group at some point as well. So make sure you're all stretching your legs, etc. But I'll open up the rooms now and look forward to seeing what you all come up with. Hi everyone, welcome back. Apologies for that. We've obviously we slightly overran, but I was very conscious going around quite a few of the groups that there were a lot of people who were sort of almost to the stage of having something kind of presentable, but not quite there. And I just felt it was a lot more value for you to actually spend a bit more time doing this. So I'm going to change it up slightly now, so that basically each group does a quick 60-second pitch. And then Sammy will have a look over the that and the models that you post in your Slack channel. So if you've got your models, I would have them ready so that you can just click play and so that when you've got your 60 seconds, you can just very quickly show it. Just quickly before we do though, just to flag up. So some of you may have seen, but if not, if I can draw your attention, Sammy has posted in the Central Plaza a link to a short Mentimeter survey. This is to find out a couple things from you. First of all, around where you all are in terms of thinking of your projects. And getting a sense of your where you are in terms of stage and where you might need support, etc. With that, and also a question about whether you want the assessment pushed back. To which I assume it'll be 100% people saying yes, but it's always good to ask. So there's an option there to delay the assessment if you so wish. Sammy, I don't know if you want to add anything more on that.
Yeah, just that we kind of were thinking about the fact that it's obviously very close, or straight after the final session, and we don't want anyone getting stressed out. I know a lot of you don't have any time outside of your allocated HSMA day to actually spend time, going through things, revising, etc. So just want to give you the option, if a lot of people would find it significantly less stressful and make it potentially more likely that you feel comfortable taking the assessment, if you've got a bit of time to actually just digest and go back through stuff, then we'd like to do that to maximize your chances of feeling confident and happy to give it a go. So we promise it's not a stressful, scary assessment, but we will also kind of just there's a space in there as well just for you to put any other comments about if you're worried about the assessment, if there's anything you need from us, etc.
Yeah, no, absolutely. Yeah, I'd echo all that. It's whatever kind of works best. I mean, from our perspective, it's not an issue. We can do the assessment whenever we like. So, it's only an optional thing. It's just for your certification. This is, we've still got 11 months or whatever it is left on the course. It's not a major issue. The reason we chose to have it there is because we thought, well, it'd be useful to have it nearer, the end of phase one. But as Sammy rightly pointed out, it might be, I don't want people to feel pressured thinking, right, well, I finished Sammy's final session. Oh, it's the assessment next week and I want to take that. Just be aware of that. We did ask this question in a year before, 1 year before, and everybody said, yes, please do push it back. So I'm aware of it, but it'd be good to get a bit of feedback on that. Okay, so in the interest of time, I'm gonna hand over now. So I'm gonna literally give you 60 seconds each just to quickly pitch your models, show them running, and just quickly talk us through it. I'll put up the timer and I'll be strict with time so that we don't overrun too much. So I'll just go through in alphabetical order. So Agnes, do you want to kick off?
Hello, I can show our model. Okay, so we tried to do the Sims. Oh, I'm not sharing yet. Now I am. We tried to do the Sims. We had it running. We had it great. We were printing out. People were eating. People were sleeping. People were studying. As soon as we've given them the option to leave, however, they leave after step 2 now. So what we've learned so far is that our Sims really don't like us. Given the option to leave, they will. But it was nice that they stayed around for at least one step, I guess. So yeah, that's where we got to.
Okay, awesome. No, thank you. First of all, hats off for you for trying. I have to say, of the 2 options this afternoon, I think that was the more challenging, and probably you've all realised why I decided against using that to teach you MESA, because it's quite a complicated model in some ways. Well done for trying it, and great that you managed to get something that runs and working, even if all the HSMAs disappear very quickly. But maybe that's just an accurate representation of HSMA teaching. Maybe I teach them all Git in week 1, and certainly that would be incredibly accurate if that were the case. Okay, brilliant. Thank you. So Antic, you're up next. Just so you're
You might be muted, you.
Yes, it's very hard to grab onto the bar when it doesn't work. It's being hidden by everything. Okay, right. So we went for the option 1, which is to create your own model based on whatever we have done from the last week. we were looking to creating where a patient would go for a treatment, and we're specifically looking for their wait time and behavior, if they're going to wait in certain location or not, and how long they're waiting based on their urgency level and their patients, but mostly patients in this case. And we could go for the model to run. So we put a bunch of patients in, and currently it's only statics as we weren't able to add quite a dynamics, but we can see the mean time of waiting, how many patients were willing to wait and how many were not waiting, but we didn't get as much further than that. But it's a nice model for now. In terms of what we're going to add in the future is dynamics for changing the queue length and potentially something related to the location and how different locations have different lengths. So
Awesome. No, thank you. That looks really good. I think that's a great sort of proof of concept. I think you're probably not far off actually adding those bits in and getting a really sort of dynamic model in there. So yeah, great, fantastic start. And again, you know, it is an accomplishment with this stuff to get the model actually running. So that's a good start there. Brilliant. Thank you. Arm up next.
Hi, we've expanded on the love-hate model from this morning and called it the contamination model, so sort of modeling contagion and pandemic a little bit. So we've got much of the same parameters, and you can see that people are starting to get infected. We've got parameter called infection days. This is modeling hours, so after 24 hours, you're no longer infectious and you become immune. And then, so I think we'll sort of start to see it tipping down shortly as people start to become immune. So that was with everybody moving. Or you can model it and see what would happen essentially if there was a lockdown, where the infection rate is a lot slower. And I don't have time to run everything, but we've also got a percentage immunised. So we worked out that high movement with high immunisation led to low spread. And also another option, which would reflect the pandemic, that if you were infected, stay at home until you're no longer contagious.
That's sorry, that's amazing. I really. How did you do that? How have you got that graph working? That's amazing.
We had to play about a bit because at first we accidentally made everybody immune after round one.
Oh, okay.
And it wasn't spreading. And also we had one where I can't remember what we did. We didn't have enough people. There wasn't enough movement for people to actually get infected as well. So we did have to play around with it to make it kind of look like it was working too.
That's a really beautiful visualization. I just love the fact you've come along and basically that's a kind of publication quality spread model. So
well, most of the comments are the ones from your original model this morning. So.
Oh, okay. Well, that's still. I mean, I'm really impressed with that. So that's some really nice visualizations. You've done amazing work. That's really good. So, no, thank you. Looks amazing. Wow. So you never know what to expect with HSMA here. Okay, so Denise up next.
Okay, try and turn everything on. Sorry, it's not wanting to share my screen, but there we go. Can you see that okay?
Unfortunately not, no.
Oh, good start.
Sorry to disappoint. You sounded so happy about it, but I'm oh, there we go. Something's coming through now.
Oh, there we go. So I failed the first test. Can't share the screen. So building on the other week's zombie chainsaw massacre, we thought we'd go for vampires this week. So we built a model where basically vampires are running around the grid space, biting humans and turning them into vampires. But then we gave them a degree of immunity as well. So if somebody was, had a certain level of immunity, that they would then turn the vampire back into a human. So you get this kind of ebb and flow between vampires and humans. And then as we were just sort of closing off there, we were just trying to introduce another kind of agent. So we were adding in a new agent, Van Helsing, down here. So So he was starting to have his own constructor, and basically, he was going to help even the odds in there. So we were just trying to build that extra class in there, but it wasn't quite working by the time we got to presentation point. But we got something working and some little wiggly charts out there.
Fantastic. Again, really, sorry, I was waiting for you to say. Really amazing stuff. Really creative. I love that. Yeah, I love the whole idea of having a Van Helsing agent. What a creative vampire slaying simulator. What wonderful creativity that. I absolutely love that. Really interesting as well that that's two groups there that have looked at kind of spread of something and potential immunization. That's interestingly. That's before this year. That's how I always used to teach the agent-based simulation stuff via. You did a disease spread model, and then what happens when you start vaccinating people and stuff like that. So it's really good for that kind of stuff. So fantastic. These are brilliant. These are absolutely genuinely brilliant. Right, Motorola, you're up next.
Hi, that's me. I'm just going to share my screen. Okay, is that okay? Is that going through?
Yeah, that's through.
Cool. Okay, so we tried the Sims one as well, but unfortunately we didn't get a model that could run. But we started by setting, creating the attributes for each agent, so one for each needs, and then a behavior related to those needs. And then those went up and down for the needs when those engaging in that behavior. But I think the problem that we got was when we were trying to set the bed capacity, we couldn't. We thought we got it to a place where we got a bed capacity that went down when people were sleeping, but then went back up when they went back from sleeping to doing something else. But we kept getting this error saying about how bed capacities, there's no value for it. So I think somewhere we didn't get it right, or we couldn't quite get to the bottom of it.
I can debug that for you now. It's just because you're referencing bed capacity as a local variable where it doesn't exist. You need to just reference wherever it is that you've stored bed capacity. So you need to store it somewhere central, and then say, a bit like we did with the discrete event stuff where we had the G class. You say G dot, it's in G. That's where it lives, or wherever it is. So
Right.
that should sort it for you. But yeah, brilliant. No, again, really well done for having a go at that one, because that was a big complex model, and I kind of chucked it out there just to see how people might. I think the key thing I wanted people to get from that was trying to work out how you convert these kind of rules into rules that you can put into an agent-based simulation. So you thought about some really nice stuff there. I really like that. So thank you. Brilliant. Okay, Paula up next.
Hello there, that'll be me. 2 seconds.
Yeah, no problem.
Right, is that sharing?
Yeah, I'm seeing more zombies.
Yeah. So yeah, we made a zombie apocalypse simulator. There could be one of two types, human or zombie. Just set that running. We have a few variables we can set: number of people, how many zombies we begin with, their effectiveness of the bite. So the lifespan is how long they can go without food. What we have here is 28-day later zombies, which can live 28 days. They're also very fast. But after 28 days, they die and drop out. Implementing that was a bit of a pain. The size of the dots indicate how much food they have left. They get smaller as they start to starve off. And yeah, we can also change the grid size, make it a bit bigger, a bit smaller. Generally, the main thing on whether the humans survive at all.
That looks amazing. Absolutely, really, really good. And again, really nice. I really like your visualization on that. I think that's a really nice visualization. You've got lots of nice user sliders there. Really sort of well thought out about the interface elements and stuff on that. So really nice use of MESA and the server stuff Yeah, I like that. Again, funnily enough, a zombie apocalypse is a kind of one of the stock models they often use to teach principles of agent-based simulation. Often you get these ones where you can watch, and you can even do stuff like get zombies, rather than randomly moving, to start gravitating towards where the humans are, and you see sort of people sort of running essentially from the zombies. So yeah.
We implemented something where the humans will run away, sort of.
Oh,
Basically, if there's a near miss, if there's an attempt at a bite,
yeah.
but an infection, they move again,
Oh,
which
cool.
quite dramatically increased the survival rate of the humans, nearly doubled it.
Wow. Okay, that's really cool. I like that. I really like that, Steve. That's a really nice feature you've added. Excellent. Thank you very much. Pokey, you're up next.
Hello.
Hi.
Let me try and share my screen. Hopefully everyone can see that.
Yeah, that's come through.
So we went with the HSMA's Sims scenario. We got to the stage about exploratory where we created a lot of data and we're going through the exploratory data analysis stage, but we didn't actually get to the visualization stage. But essentially, we created what was in the brief. We coded in some behavior where they would actually seek the environment where they had the lowest score. So if they were studying, eating, sleeping, or socializing, whichever was the lowest, they would seek that environment unless it wasn't, and then they go somewhere else. And let's just run this very quickly. And we haven't got to the stage of bringing up graphs yet, but what we can see is that we've got here up to 50 HSMAs, up to 20 beds, and then we're just going through a phase now where we can try and identify the optimal sleep pattern. And it seems here that the optimal pattern is to have 8 beds and 5 HSMAs.
Fantastic. That's absolutely amazing. Well done. I mean, as I'm sure the other groups who attempted this will attest, and I can attest that this was not a simple task. You know, I went through this process and thought there's a lot to think about here. So really well done for not only managing to code that up, but also starting to get results out. So absolutely amazing. Really well done. In the time you had, that's really, really impressive. So fantastic work. Excellent, thank you. Sid up next. I didn't skip anyone, did I? You were Pokey before, yeah.
Right, yeah. So we also looked at infections. We didn't get nearly as many variables in as some have, though. But we did manage to get the batch workings, which gives us the amazing revelation that large population densities are bad for infection. But yeah, so we played around with people traveling far distances, so plane travel and things we were thinking about. We started talking about things like mortality and infection control being wrapped into that as well. But yeah, as I say, without a doubt, the biggest impact we noticed was that cohort size. But yeah, we were looking at it from a perspective of that rather than having one single event which would infect you, we looked at it from an overall exposure level, which is what this is looking at here. So the higher your overall exposure, the more likely it was that you would be infected when you took your test strip in the morning or whatever.
Fantastic. No, amazing. Really good. What I really love about this as well is that you thought about looking at sort of things like your sort of exposure levels. I think that's really, really interesting outcome, but also the way in which you were modeling, and I think I sat in while you were coming up with the logic for this, but the kind of maximum distance traveled, that you had this concept of people sort of moving essentially to another area in your environment, potentially sort of taking the disease with them, and sort of the way in which you model that, and that could encapsulate people getting on sort of public transport and going somewhere else. And that was really nice. I really you thought about some really interesting sort of dynamics in that. So that was a really nice example. Brilliant. Thank you very much. TIA. I know you got something working at the last
That's
second.
me. I got it working. I'm showing you the optimized version. So let me see if I can get it going. So can you see?
It's just coming through now. I think there it is. Yeah.
Super. So we followed up on our Glastonbury model. Yes, Glastonbury model. And so really we were trying to look at the behavior of festival attenders, whether going to the stage or going to the stall, and which stall they preferred. But we stalled on the stalls. So really we've managed to model what happens when they reach Glastonbury and their decisions to go to the toilet, to go and watch some music, or to go and eat some food. Now, what we did, which is quite different from other people, is our grid model was just a 1x4 grid in which we decide which position each cell is a position. So here you can see that orange is stage, red is stalls eating food, blue is going to the toilet. And if you look here in the code, what we did is that if you go to the toilet, your need to the toilet goes back to 0 and then progressively increases if you're waiting for food or if you're going to the stage. And likewise, if you've gone to a stall to get some food, your need to food goes back to 0 and gradually increases as you wait. And so we get this quite dynamic behavior of people going from stage to toilet to stall.
I really like that. Thank you. That's such a simple but effective visualization you got there as well. And the nice thing about this stuff as well, you could imagine just sort of feeding that out externally to MESA and having a really nice sort of graphic that sort of shows that simple dynamic of people congregating in different areas. But yeah, I like the fact you've done that, and the fact that you've kind of integrated elements of individual needs of the agents, etc., and watching those change over time. So yeah, really nice, really simple but effective visualizations there that look really good. So thank you very much. Brilliant. And then last up, we got Zylog.
Hi.
You'll need to stop sharing. Sorry. Oh, there we go.
Hi, that's me. So we took the idea that we had last week and we thought we'd run with that and try and see if we could actually turn it into something real.
Okay.
So we have a concert hall, which has a stage down at one end, has an exit at the other end, has a bar and a toilet. And we have agents within that concert hall. And we also have various other parameters that we don't have on sliders yet, for instance, things like music quality, which will determine how much you want to get to the stage. And then depending on how good the music is, you'll want to get to the stage much more. We're tracking here average happiness, by the way. And what we found is one of the things that was interesting that we came to with this was that we weren't modeling our agents that they would actually get a full bladder and then go to the toilet. We were modeling that they would find the toilet more attractive if they had a full bladder. But nonetheless, it ended up with a pattern where the stage and the toilet was the main attractor. Now, of course, we could increase the quality of the beer, in which case the bar might be more of an attractor than the toilet. And so we're playing around with those various parameters to see which one is the most attractive thing.
That looks amazing. I really like that. What a fantastic visualization as well. Again, just using that standard sort of stock visualization, how powerfully effective that is. Just showing that sort of crowd dynamics. And I really like the idea that you have these kind of attractors that sort of gradually. It's also a gravitational model where you're sort of gradually pulling people in. But as you say, it just becomes an attractor. But you've got other sort of competing attractors as well. So yeah, really well thought out. Really like that. And again, another superb visualization that we've seen this afternoon. Pretty impressive, considering in 2 hours, considering you only learned how to do all this morning, that you've all managed to come up with these amazing things. So obviously, I'm guessing, Sammy, you'll need a bit of time to go through these. But anything you wanted to add at this stage?
No, equally just yeah, blown away. There's so much good stuff in here. I would love if people would be willing at some point. I think it might be really nice for us to, a bit like where we've had the other HSMA books, if we could collate some of these models into a bit of a library of examples, because there's so much good stuff here that would, I think, really helps people think about the different ways to structure models. There's such nice examples of different ways you've approached things that are more low kind of grid-based, things that use grids in creative ways, and hopefully that would be a useful resource for you guys as well to come back to over time. So I'll kind of explore some opportunities for ways we could work with that if people would be happy for their code to go into that.
Yeah, no, definitely. I definitely agree with that. I think that would be really cool. And I think, as I was watching these things, thinking, how have we managed to do this? That it'd be interesting for me, and I think it'd be interesting for a lot of you, especially those of you who are thinking about potentially going on to an agent-based simulation, these different ways in which you can approach these problems. And what was striking, I think, other than the sheer quality of the stuff we saw, was just each group sort of brought a really interesting perspective into the problem that they were tackling. So it was really interesting to see so many different ways of approaching this. I think you absolutely all nailed that sort of creative design process that's so important for agent-based simulation. So I'm really, really pleased you've done that. I've been absolutely elated to go around the groups this afternoon and hear so many people enjoying themselves and really enjoying playing with agent-based simulation. So that's really good. It is I always find it a very fun modelling method to work with. So it's been great to hear so many people really enjoying this. So I'm really looking forward to seeing potentially more agent-based simulations. I'd love to see some agent-based projects. I think I can't wait to see if you can come up with that in 2 hours. I mean, goodness knows what you come up with in 9 months. So fantastic work, everyone. Okay, apologies yet again. I mean, I don't know why I'm bothering to say. I always run over now. So apologies. Only the 19 minutes today. But I'm glad we did, because I'm glad you had that extra time to do that. So next week will be my final training session before Sammy takes over for the bulk of Module 7 and for all of Module 8. Obviously, I'll still be here, but I'm going to leave you probably with a bitter taste in your mouths as I teach you Git, which, for those of you unfamiliar, you're all going to hate me in a week's time because Git is horrible. It's very, very important. It is incredibly important to version control your code, but I am not going to lie, it's horrid. So there's a reason we try to push it as far back as possible. I say that now because I don't want you coming into next week thinking, why am I struggling so much with this? You'll all be in the same boat. So just bear that in mind. I will send out instructions tomorrow on what you need to do. Primarily, it's going to be, there's nothing fancy to do in Python. You just need to make sure that Git is installed, and you'd better hope that your IT department has unselected Vim as being your default text editor. I can guarantee some of you will not be in that position and will find a very entertaining situation next week where you can't work out how to get out of a message. That's all the fun that's going to come next week. Sammy, anything you wanted to add before we close off?
Just please do respond to the survey, really helpful to us. And don't forget, there is a project development clinic tomorrow. Please do come along if you want to chat about your projects. Also, we're kind of still exploring what best to do for the scheduled revision sessions next week and the week after. We think it might be more useful to some of you to have a sort of space to actually talk about your projects instead, a bit more of a chance to sort of tease out how, some of the questions you might have, or if you are a little bit stuck for ideas, to have a chance to sort of discuss in a smaller group some project ideas and next steps and ways you can engage with stakeholders and stuff. So watch this space. There will be some updates on those sessions coming very soon.
Yeah, brilliant. Thanks, Sammy. Yeah, apologies, I forgot to mention that. Yeah, so project development clinic this morning. It is in fact the final project development clinic. But obviously, do still keep, even if you can't make that, be posting on the ideas forum. And actually, some of you may even over the next few weeks want to start registering your projects. So don't forget the process to do that. You simply log it in the airlock, explain what you want to do, and we will register it as a project for you. But if you're still a bit unsure and you want to shape it, put it in the ideas forum, or come along tomorrow, or do both, and we can try and nudge you in the right direction and get you thinking in the right way. But I'm really looking forward to seeing what amazing projects you come up with over the coming weeks. Brilliant. I will stop talking because we're now 22 minutes over, and I look forward to seeing you all next week when we're going to have fun with Git. See you, everyone.